Hi, I'm Aaron Packman. I'm a professor of civil and environmental engineering at Northwestern University and the director of the Northwestern Center for Water Research. I'm very happy to welcome all of you today to the second day of our symposium on water in Israel and the Middle East. And the focus of the symposium this year is on water innovation between wet and dry lands. So we've had a number of years of this event really exploring water needs and water solutions for arid regions. But this year, we're celebrating the formation of the Great Lakes Water Innovation Engine, which is a new $160 million large regional project that's funded by the National Science Foundation and led by Current Water Innovation in Chicago. So most of our speakers today are part of Renew, and we're featuring a lot of water technologies that can be developed here, deployed in arid regions and around the world. We will also have some discussion of results from the Collaborative Water Energy Research Center, COWORK, which is a binational effort. And so we'll hear some interesting things that are happening in Israel that also can be applied in the Great Lakes and across the world. I'm now going to turn things over to my colleague, Eric Perreault. Eric is a professor of biomedical engineering from Northwestern, a long-term colleague. He'd been the associate dean in the McCormick School of Engineering and is currently the vice president of research for Northwestern. Eric.
Thank you, Aaron, for that nice introduction, and welcome to all of you. It's really a pleasure to have you here for the 8th annual Northwestern Water Symposium. And as looking over my remarks for today, I was stunned at how many symposia we've already had. It seems like not too long ago since Aaron launched the first one. So this year's theme, innovation in wet and dry lands between Great Lakes and the Middle East, really represents the universal nature of the problems that you're attacking. And so I'm really looking forward to an enlightening day with discussions that cover a broad range of topics relevant to all of us. So Northwestern is really proud to be a co-sponsor of this event with our esteemed partner Current that Aaron mentioned earlier to you. The program was also shaped tremendously by a few people at Northwestern that I'd like to point out, particularly Aaron, who's really done a tremendous job with the Center for Water Research. The Center for Water Research exemplifies Northwestern's interdisciplinary nature. Not only do we have faculty from civil and environmental engineering, we have faculty from business school, from chemistry, from environmental science, policy, and law. And it really allows the center to look at a range of interdisciplinary problems. And for that reason, it's actually part of my office in the Office of Research. It's one of the 35 interdisciplinary institutes and centers at Northwestern University. Excuse me, the second person I'd like to acknowledge is Eli Rekas, who is the leader of our Israel Innovation Project, which is another tremendous group at Northwestern University, and it really symbolizes how Northwestern focuses on interdisciplinary work across the globe. Another measure of that is our work with Current, which, as Aaron mentioned, is a regional engine. Current was formed in collaboration with Northwestern and some of our other partners in the region. Aaron played a wonderful role in that. And I think you can see that Current has had a tremendous impact on what this region and what partnerships between Northwestern and our other colleagues across the Midwest can do. Current now is, without a doubt, I think, the leader in water innovation in the Midwest. I wanted to talk a little bit about the Great Lakes Renew project that Aaron mentioned. So today's symposium is the first since the Great Lakes project was announced and awarded. This is one of 10 regional engines awarded across the country, and this was an incredibly competitive competition. And I just wanted to describe the engine in the words of our current National Science Foundation director, who said that the engines program represents one of the single largest broad investments in place-based research in our nation's history, and the development, and it uniquely places science and technology leadership as the central driver for regional economic competitiveness. So this is a really nice example, again, of partnerships between academia, industry, and government. And this partnership has really come to a head in Illinois with our current governor, J.B. Pritzker, who's really been a champion for initiatives like Great Lakes Anew and many others across science and technology, looking to make Illinois a leader in science and technology for the benefit of mankind. So this year's symposium draws a significant parallel between the Great Lakes and Israel, lands that are very different, yet share common problems when it comes to water. And as in past events, the symposium employs a transdisciplinary collaborative approach to looking at these problems. So in addition to Northwestern, we have colleagues here from UIC, from Purdue, from Argonne, from the Rapid Manufacturing Institute, from Mekorot, or Mekorot is probably a better pronunciation, Israel's National Water Company. And I extend my gratitude to all of you who have come here today, particularly those of you who came from Purdue, who probably had the longest travel if anyone's here, or they may still be stuck in traffic having to go through Chicago on a rainy day. But in any case, I just wanted to end by thanking all of you for being here. I hope you have a really productive day of discussions. I heard yesterday was a nice event, and I'm sure today will follow up with much more. So thank you for your time.
Thank you, Eric, for that very nice introduction and a good reminder that truly water is interdisciplinary and that we are seeking broad cooperation and collaboration to solve important global water challenges. I'll transition now. I have just a real quick logistical note. So there's, of course, food and coffee outside. The internet is here. So you can either use the UChicago guest network with the username Northwestern and the password GZIZ3. Or EduRoam works here also. So if you have connected to EduRoam from the university, it should work automatically here. Now we'll switch to our first technical session. And unfortunately, the first scheduled speaker, Ignacy Paulo Rivera, was unable to travel. So we found out a couple of days ago he wouldn't be able to be here. And instead, one of my co-organizers, George Wells, was perfectly willing to step in and help us and agreed to give this first talk. So I'll introduce him now. George Wells is a professor of civil and environmental engineering from Northwestern. He's Northwestern's principal investigator for the Renew Regional Engine. So he's highly involved in a number of collaborations, both across the region and with collaborators in Israel.
Very good. Thank you, Aaron. Really a pleasure to be here, to be part of this important conversation. Really looking forward to the day. What I want to talk to you about a little bit to sort of kick off the symposium this morning is a broad overview, let's say, of some of the work that we're doing at Northwestern with our collaborators, with partners towards a sustainable and circular water economy, really trying to delve into this area of inquiry, targeting collaborative advances at the water energy nexus for the Great Lakes and for the Middle East, Israel and the Middle East. This is not going to be an overly technical talk. We are going to delve into technical details, I think, in subsequent talks for technologies being developed through CoWork and through Great Lakes Renew. This is going to be a bigger picture talk. I'm going to try to talk a little bit about motivations for water innovation and some of the larger scale efforts that we have at Northwestern and in the region as well. So roadmap for today, I want to talk just a little bit about water circularity and the water energy nexus. Then I want to talk just a bit at high level about the role of technological solutions, in particular some of the work that's going on in CoWork and in Great Lakes Renew that we're just getting off the ground. We'll hear a lot more about throughout the day. And then I want to wrap up just with a couple of minutes to try to make a pitch for the role of water technology collaboration in driving geopolitical cooperation. I think there's a really key role here, and I think that's one of the drivers for many of us in this area. So let's begin just a little bit of framing here. Water systems that we use pretty much globally, urban water systems, are usually effective to a certain degree, to a large degree, I would say, at producing clean water, but they're largely designed for a 20th century paradigm that focuses on linearity. So kind of this take, make, waste model of water extraction, use, and discarding wastewater, separation, uniformity, and centralization. So just a little schematic of high level our use of water in society. We focus mainly on extraction of water from very high quality traditional water sources, lakes and rivers, high quality freshwater sources, groundwater as well. We subject this to potable water treatment using a range of very common unit processes that are relatively effective. We produce very high quality water, drinking quality water. We use most of that water, the vast majority, for non-drinking water purposes. We also use lots of chemicals. We produce high volumes of residuals, and we use energy-intensive processes in these drinking water treatment, this potable water treatment scheme. We use that water in society. We produce lightly used water that we call wastewater. It's not a term that I really like. We call it wastewater, but it's really just lightly used water. We treat this water in conventional wastewater treatment plants that are highly energy intensive. They're prone to production of greenhouse gases, like particularly methane and nitrous oxide. These are microbially produced greenhouse gases, and they produce high volumes of residuals. And then by and large, we release that water to a receiving water body. So linearity, that's pretty obvious. Separation of drinking water from wastewater, that's a foundational element of 20th century water engineering that I think we very much need to reevaluate. And we certainly have in places like Israel. Uniformity, uniform application of some of the same technologies everywhere in the world rather than designed for local conditions, and highly centralized water infrastructure. I want to zoom in just a little bit on the energy intensivity of wastewater treatments. This is what I think about quite a bit in my own research group, and I want to highlight the fact again that conventional wastewater treatment is successful, at least mostly from the standpoint of removal of our classic water pollutants, BOD and nutrients. We can do a pretty good job, but it's very energy intensive and very resource intensive. Where is that energy used? Wastewater treatment in the US alone accounts for about 3% of nationwide electricity use. Most of that energy, there's actually quite a number of different sinks, let's say, for energy, but a very good proportion, by far the majority of, or the largest share of that energy use is used for oxygen supply to drive microbial metabolism, aerobic chemoorganoheterotrophic microbial metabolism, basically bubbling air into water. That's where the energy goes to, which is a little bit interesting that that's where we're sinking our energy into. What's paradoxical here is that when we look at the energy potential, just the chemical energy potential in wastewater, what we find is that there's a lot of potential energy there. We're expending lots of energy to remove actually energy-rich compounds from wastewater. If we widen our umbrella for what we think of as wastewater, and we include organic-rich municipal, industrial, and agricultural wastewater, the estimate in the US is that the chemical energy potential, this is not including thermal energy, just chemical energy potential, is about 17 gigawatts of power. So a bit of a paradox here. We have an opportunity, I think, to flip this industry on its head, to move from an energy-intensive industry to potentially an energy-neutral or even an energy-positive, energy-producing water sector. And this really underlies what I see as a paradigm shift that is ongoing in the water sector towards resource recovery, moving from this linear processing of water. So again, just a simplified schematic of how we deal with wastewater in society at present, most places in the world. We have wastewater that we send with organic matter and nutrients to highly centralized wastewater treatment plants, expend quite a bit of energy and money to produce clean water, and by and large, we release that to a receiving water body. Increasingly, it's recognized that this is an example of misplaced resources. The organic matter, the nutrients, the water and wastewater, these all have potential value, and it behooves us to, as a community, to move towards energy-positive water resource recovery by rerouting these misplaced resources and closing the engineered water cycle, really moving towards water circularity. So just a very high-level schematic of this vision that drives much of what we do in my group. We have used water. Again, this semantic reframing is very important in my view. It's not wastewater. It's just lightly used water with organic matter and nutrients. We send this to, I'm an environmental biotechnologist, so I like to think about biorefineries, but we can also use physical chemical processes as well to extract energy, nutrients, materials, platform chemicals, maybe metals and minerals as well, and of course, clean water. And where it makes sense, we reroute that clean water for reuse. And this vision of water circularity and resource circularity really drives a lot of what we do in my group. It also drives, I would say, much of the innovation, collaboration, and technology sharing that we're seeing in the water sector at this point. I'm going to mention two other drivers that I think, in my view, underline or drive a lot of this innovation at present. The second driver is a move towards decarbonized water systems that is addressing the greenhouse gas footprint of our water sector. and climate-independent water sources. So really, this is an example of climate change mitigation and adaptation. What do I mean by climate-independent water sources? I mean moving away from a focus just on our traditional, very high-quality water sources to alternative water sources, things like seawater, wastewater, saline groundwater, and the like. And then, of course, one of the major drivers that we're going to hear more about later today is mitigation of non-traditional contaminants, micropollutants, things like PFAS, pharmaceuticals, personal care products, and the like. I want to focus a little bit now on the role of technology sharing and collaboration, transboundary collaboration. And I want to highlight some of the achievements in practice in Israel over the last couple of decades, in particular highlighting the role of Israel in identifying and accessing non-traditional water sources. And I'm going to show you a couple of plots that come courtesy of Israeli collaborators, and I find really amazing, just very promising. The first one, we're looking at the adoption of seawater reverse osmosis-based desalination in Israel. You're looking at a plot of starting in 2000 and then projected forward to 2060. And that's on the x-axis. On the y-axis, we have the total volume per year in million cubic meters per year of seawater reverse osmosis desalination, water derived from seawater. And what you can see is over the last 15 or 20 years, this number has gone from quite low up to about 75% of Israel home water use. So from a negligible percent, a very small percent of Israel home water use, to 75% in about 15 years. That's an astonishing shift in my mind in what is traditionally a relatively slow-moving sector of society. To have this dramatic shift in water source, this accessing of an alternative water source via cutting-edge technology implementation over a very short time period. What's even more interesting and surprising to me is that Israel has really led the way in not just accessing seawater for a single use, but kind of double dipping in that same water in terms of water, wastewater reuse. So we're looking at agricultural irrigation, water for agricultural irrigation in Israel. And we'll probably hear more about this, I think, later today a little bit. So just a high level, let's say a preview. We're looking at year on the x-axis, 1960, projected forward to 2050. And we're looking again at million cubic meters per year of water for agricultural water consumption in Israel. In green, we have water derived from potable, high-quality freshwater sources. The really interesting portion here, we do have brackish water, which is quite interesting. But here in yellow, we have wastewater effluent. This is water reuse after municipal or industrial use. And you can see starting in the mid to early 1990s, Israel really adopted a strategy of trying to capture essentially all or nearly all of the wastewater that has been produced in the country. In Israel, over 85%, I think it's close to 90% now of wastewater is reused, which is astonishingly high. That's the highest by far of any country in the world. I think number 2 is Spain, if I'm not mistaken, which is around 20% or so. Spain or Singapore, yep, exactly, but much, much lower percentage. So this is really quite astonishing, and again, in quite a short amount of time for at least for the water sector. So I want to highlight big picture collaborations now that I think are helping to drive technology advancement, technology sharing, and collaboration, transboundary collaboration. The first thing I'll highlight is the Israel-US Collaborative Water Energy Research Center, or COWORK. This is a center that is co-led by my colleague Aaron Packman here at Northwestern. And then in Israel, it's led by Moshe Herzberg at Ben-Gurion University. It includes a number of different universities in the US and in Israel, a number of different utilities, and a number of different companies as well. And the overall focus of COWORK, the mission, is to leverage recent advances in both the US and Israel to reduce the energy intensity and the cost of water across the entire water spectrum. There are 3, let's say, key pillars of the work, the collaborative work that we're doing in COWORK. One is energy efficient enhanced water supply. Much of this focuses on material development and reverse osmosis-based treatments. The second is water reuse and resource recovery. This is really my bread and butter. This is what I think about all the time. And then we have a focus on integrated energy water systems, really using systems analysis to understand environmental and techno-economic impacts of technologies. This center has been in operation for 4 years. Am I getting the time? 4 years now, and has achieved some really amazing goals over that time period. I'll highlight a couple of the technologies in a minute, but I do want to draw a connection here to the new center that Eric and Aaron mentioned, Great Lakes Renew, which is also to some extent a transboundary water innovation center. It's trans-states, but I think we're trying to develop technologies that really address problems that are certainly regionally relevant, but also globally relevant, right? So the NSF Great Lakes Water Innovation Engine, this was just funded. It's led by Current, which is a water innovation hub here in Chicago. The mission of Current is to discover, develop, and deploy innovative technologies to decarbonize water and wastewater systems and recover valuable nutrients, critical minerals, energy, and water from wastewater. So water resource recovery, moving towards this goal of water circularity. Very strong synergies between these two systems. The tagline, which I really like, is from waste to wealth and health, built in the Great Lakes, made for the world. So we're addressing regional issues, but we're really trying to do so in a way that contributes to solutions of water issues globally, right? So I'm just going to highlight a couple of technologies at high level. I'm not going to go into any detail about the technologies for the sake of time. We'll get more technical details later, but a couple of these solutions that we're pursuing in CoWork and in Great Lakes Renew. The first thing we're trying to do is we're trying to solve this issue of the massive amounts of energy use in traditional wastewater treatment that derives from oxygen supply, that about 50% of energy use that comes from just supplying oxygen to microbial bioprocesses. One of the areas that our Israeli counterparts are focusing on, this is at Ben Gurion University and at Chaplin, water reclamation plant in Tel Aviv, is using an anaerobic process, emitting completely the addition of oxygen to the system, moving towards a mainstream anaerobic process where we capture value from organic carbon in wastewater, mainstream dilutes wastewater, domestic wastewater, via a so-called membrane biofilm reactor. This is a mixed culture microbial bioprocess where we think we can produce energy via biogas generation, so elimination of aeration, but also energy capture, and relatively clean water, low organics water. We do still have nutrients in that water. That can be a good thing for water recovery, depending on the application. In many cases, though, we want to do something with those nutrients. We may want to remove them or recover them. So another area of focus, very quick example that I'll give you, is a microbial bioprocess that we've developed here at Northwestern called the CANDO plus P process. The basic goal of this process is to take the water that comes from anaerobic treatments, low organics, high nutrients, and recover those nutrients as value-added products. In particular, what we're interested in doing is recovering the nitrogen as an energy molecule. We're looking at nitrous oxide as an energy molecule with the goal of both producing nitrogen-based bioenergy and also completely eliminating emissions, fugitive emissions of nitrous oxide. We also produce clean water for reuse, and we engineer the microbiome in the system so that we think we can also recover phosphorus from wastewater as a fertilizer as well. So that's a very quick example too. The third example that I'm going to give you, and I'm just sort of touching on a little palette of technology options here. Happy to answer questions and go into detail, but just giving broad brush overviews of these options, is a much newer project. This is actually aligned with the Great Lakes Renew efforts, where we're seeking to develop completely new ways to recover dilute nitrogen from wastewater as value-added products. What we're particularly interested in is an underexplored bacterial biopolymer called cyanophycin. This is a nitrogen-rich biopolymer that we think may have promise as a platform for nitrogen bioconcentration, partitioning, and recovery. What have we done so far? I'm going to show you just a little bit of data here because I'm really excited about this project. What we've recognized so far is that the metabolic pathway for cyanophycin production is recognized, has been documented in a handful of model pure culture bacterial taxa, right? So bacterial taxa studied on their own in the lab. What we don't know is its relevance in mixed culture systems and its potential as a platform for resource recovery. In fact, the first question that we wanted to ask is, do microbiomes in existing biological nutrient removal systems at wastewater treatment plants actually already have the capacity to accumulate cyanophycin? We turned to a DNA and RNA sequencing approach to look at this. Not going to go into technical details about how we did this, but basically we retrieved quite a number of what are called metagenome assembled genomes. These are genomes of bacterial taxa that are present in existing wastewater treatment plants. And we asked, of these metagenome assembled genomes, can we document the presence of metabolic potential for cyanophysin? What we found is that about 25% of the metagenome assembled genomes that we recovered had an indication, an annotation for cyanophysin production, which is quite surprising. That's quite high. Even more surprising was the fact that we documented the presence of metabolic potential, so in the genome, for cyanophysin production in a couple of the functional groups that are very important to driving overall performance in enhanced biological phosphorus removal and biological nitrogen removal systems. For example, so-called polyphosphate accumulating organisms. We also took a look at some gene expression data, metatranscriptomic data this is from a lab scale reactor, an enrichment reactor from our lab for this key functional group, polyphosphate accumulating organisms. And we showed that these cyanophysin pathway genes are not only present, but they're expressed at a very high level. So to me, this is quite promising. I do want to emphasize this is very low on the technology readiness level scale. This is early stage research, but we do think that this is quite promising because it shows that metabolic capacity for cyanophysin accumulation may be surprisingly widespread, even in existing biological nutrient removal processes. And because of that, we may be able to use existing infrastructure as a platform for nitrogen bioconcentration, partitioning, and recovery. So hopefully more to come on this line of research in the years to come. If I can, for about 2 more minutes, is that okay? Can I take 2 more minutes? I'm going to switch gears, and I just want to make a pitch at the end of my talk here for water technology, collaboration, and innovation as a mechanism for geopolitical cooperation. I think there's a huge amount of promise here. I think we're doing this already, and it's something that we can really build on. I'm showing you a picture on screen here of a really fun expedition. This is a global engineering trek that I participated in. I co-led with, well, Ellie was the lead, and I was the sous chef, let's say, on this expedition. This was a year and a half ago or so. We took a group of about 14 students from Northwestern to Israel, toured a bunch of different water related installations, learned a lot about water infrastructure. We met with a group called EcoPeace Middle East, which is a fantastic nonprofit based in Tel Aviv, Ramallah, and Amman. So Israel, Palestinian Authority administered areas, and Jordan. And the goal of EcoPeace, the mission, is to develop environmental solutions to transboundary environmental problems like water problems. And one of the things that we talked about in this meeting was the hyper-local nature of water challenges in Israel and in the Palestinian Authority administered areas and in the Middle East in general. This also extends to many other parts of the globe as well. So just an example of this, we're looking at a map of Israel. A little bit hard to read here, so I'll point out towards the bottom of the screen here. Here's the Mediterranean Sea. Here's Tel Aviv. This is Ashkelon right here. Ashkelon is the site of a desalination facility that produces around 108,000 meters cubed per year of fresh water from seawater via reverse osmosis. It's one of the most advanced water supply facilities in the world. A really impressive cutting-edge water technology put into practice. About 3.5 miles south of Ashkelon is the border with Gaza. The length scales are amazing in Israel, just very, very close, 3.5 miles south. What we traveled about 5 times that distance from Evanston to come downtown today. So very short length scales. And of course, Gaza has experienced severe water challenges for years, including both on the drinking water side and the sanitation side. Just a little bit more about this. It's estimated that about 4%, less than 4% of domestic water supply in Gaza is fit for human consumption based on WHO guidelines. And what I find really interesting is the fact that, so this is focused on domestic water supply for drinking water. There's also relatively poor sanitation as well, lots of untreated wastewater that's released from Gaza as well. Water, of course, does not recognize political boundaries. So the water from Gaza, particularly from northern Gaza, Gaza City, untreated wastewater, goes into the Mediterranean Sea, which of course is the source of drinking water for the Ashkelon desalination facility. And there have been instances where, because of prevailing currents, et cetera, that untreated wastewater release has impacted operation negatively at the Ashkelon desalination facility. So as an engineer, a water quality engineer, I want to point this out. I'm looking at this from a glass half full standpoint. I think this is a clear opportunity for hopefully future water technology sharing, collaboration, and solutions for water crises, hopefully to promote geopolitical cooperation as well. So I'll put that out there for discussion. I think many of us got into this field because we're interested in solving transboundary water problems. I think this is one area that we can maybe contribute. So with that, couple of takeaway points to wrap up. I think I am a little bit over time already here. So take-home points. Hopefully I've convinced you that innovations in water technology are accelerating the transition to a circular and sustainable water economy in the Great Lakes region, the Middle East, and beyond. We touched on energy, nutrient, and water recovery and reuse, decarbonized water systems, and then non-traditional water sources like seawater and wastewater. And finally, I wanted to make the point that I think at least research and innovation in water technologies offers a key opportunity for transboundary water collaboration. So with that, I'll thank my group. A couple members of the group are here, which is great, and sponsors of some of the work that we're doing. And I'll take any questions.
So please use the mic because it's a hybrid meeting, especially students from Evanston.
Oh yeah, we're
are
on Zoom right
listening
now.
in.
Yeah.
Pointed, I talked.
Yeah.
No.
Yeah.
You had a stat early on in the presentation about how Israel is using 90% water efficient. I mean, it was just,
Yeah,
it's down.
85 to 90%. Is that
If
is
that
right for us?
happened
Yeah.
here, what
Yeah.
would that mean? What would that look like?
Yeah. So that's actually a really interesting question. In the Chicago area, in the Midwest in general, of course, we're a water-rich area. So water reuse is almost, I don't want to say non-existent, but it's very rare, right? So it's an excellent question. I think that's a research question. Where would we use that water? I think probably in industry. Maybe from my perspective, putting everything else aside, wastewater with nutrients entrained, what's often called fertigation, is a great use for water reuse. If we can use it in agriculture, that's great. The challenge is getting water, low quality water from where it's produced in cities to agriculture. It's a long distance, right? So I think there are some possibilities,
For
but it's
extra
challenging.
credit.
Yeah.
Um,
But if I could just say, the answer is quite different if you look at California or Arizona, et cetera, where this is already happening. Not at the same level as places like Israel, the Middle East, but it is happening quite.
That's kind of where I
Yeah.
was going. So,
Yeah.
you know, there are cities like in Nevada, there are places,
Absolutely.
different places. What would our country look like if we were more efficient with water?
Yeah, overall, it would be a much more sustainable country, especially in the West and arid lands for sure. Where should water be reused? That's a bit of a tricky question, but in many places we are or we're moving towards potable water reuse, right? Which really needs to happen, I think, especially in the West. But there are many different places where water is reused. I learned actually recently there's water reuse on the Northwestern campus in a couple of different buildings, the Kellogg Global Hub and our music school. We have gray water reuse for landscape irrigation, actually, which is quite interesting. Yeah, good question. Thank you.
Hi, great talk today. Thank you so much. My name is Mariana Sparopoulos, and I'm a commissioner at the Metropolitan Water Reclamation District. So thank you to our friends at Current for the great work that they do, because we partially fund that.
Yes.
But to talk to your water reuse point, we have delved into that area several years ago, And just a point of reference is that communities look to the sale of water as a large part of their budget. And that is where the pushback has come from. So the person who asked about where would that water be used, we approached industry.
Yeah.
They were very much interested in that, but there was pushback from communities that rely on that income.
Yeah.
So that's the point that we have to look at when we, start initiating those conversations again. But
Very
great
good point.
conversation today. Thank you so much.
Yeah, excellent point. Thank you.
Thanks for the talk, George. I had a question regarding your nitrogen accumulating bacteria.
Mhm.
So I know you said this is really very early stages, kind of just exploring the feasibility. Have you thought about how you would actually recover that from the bacteria? Because I would presumably you'd have other bacteria that wouldn't be accumulating this molecule. Maybe
Right.
Just talk a little bit about that, please.
Yep, absolutely. Yeah, so it's a quite interesting polymer. It produces what's called a cyanophysin peptide granule. So it's kind of a solidified, you can see it under a microscope in the bacteria. It's also selectively soluble, so a pH swing can solubilize under low pH cyanophysin. And then if you swing back to higher pH, you can precipitate it. So there's actually a pretty clear route. This is actually one of the areas that we're working on with another collaborator. A fairly clear route. We have to see if it makes sense in the end, but a fairly clear route for separation and then recovery. Yeah, good question.
Okay, I have one last question from Zoom.
Yeah.
Hi, Professor Wells from Justin Spitz. Great presentation. I was wondering if you had a sense of how the cost of water is changing in the Great Lakes area. There's an abundance of water here for now, but are prices changing? Also, are wastewater discharge rates changing?
That's an excellent question, and I think maybe you would be better placed to answer that than I don't know. I don't know what the long-term trajectories. Yeah. I don't know off the top of my head either. That's a great question. Yeah.
Thank you very much, George. So let's thank George again.
Thank you.
Especially for giving such a nice talk on 4 days advance notice, putting it together and giving a great overview of some of the challenges that we're facing, some of the opportunities and potential solutions. The next speaker today will be Meltem Urgun Demirtas, who is a colleague from Argonne National Laboratory. Meltem is the lead of sustainable materials and processes at Argonne. She's also leading a number of regional efforts and some national efforts around energy recovery, wastewater reuse, and bioenergy technology. And that's what she'll be discussing with us today.
Yes. Good morning. I would like to thank George West for establishing a nice layout for my presentation. Thank you, George. So my topic is mainly focusing on high-strength wastewater treatment, why we are focusing on high-strength wastewater, or how should we define the high-strength wastewater. It is considered if the carbon oxygen demand is more than 4 grams per liter is considered as a high-strength wastewater. So when we look at the wastewater characteristics, chemical oxygen demand is changing between 2 grams to 50 grams per liter. And when we look at the many industrial operations, for example, if we are going to produce 1 liter of beer, that means we have to dispose or we have to treat 3 to 10 liters of wastewater. Or if we are going to process 1 liter of milk, so to produce cheese, for 1 kilogram of cheese, we need to deal with minimum 4 liters of wastewater generated from cheese production. So on Friday night, when you are drinking your beer and eating your pizza, please think those numbers. They are very high. We have to deal with it. And their treatment, unfortunately, put a big challenge on conventional wastewater treatment plant operations. So we all know that there are 2 types of, mainly 2 processes that we are talking about. aerobic treatment. When we look at the aerobic treatment, it has high treatment efficiency, but also it requires a lot of energy. When we look at its startup, it usually takes about 2 to 4 weeks, so which is good. It is very friendly in terms of startup, in terms of operation. They are not temperature sensitive. On the other hand, when we look at the nutrient requirement, it is high, so we need to always consider carbon, nitrogen, and phosphorus balance. So when we look at the resource recovery in terms of energy or nutrient, unfortunately, aerobic treatment is not friendly for us. So when we look at the anaerobic treatment, when we look at the anaerobic digestion treatment, they require less energy input with potential of recovering carbon in the form of bioenergy, as well as recovering the nutrients. When we look at the effluent quality, it is not great as much as with the aerobic treatment, treated water. And the good news is that with this treatment, we can produce less sludge, which is good. So because it helps us to reduce the cost of the sludge treatment. On the other hand, startup time is really higher than the aerobic treatments processes. It is ranging between 2 to 4 months. And also we need to consider consider about the other issues with the anaerobic treatment processes. So when we look at the anaerobic digestion of organic complex matter, it usually happens within 4 steps. Hydrolysis step is really needed for soluble organics production from highly complex organic matter. Then it is followed by acetogenesis, which results volatile fatty acids ranging between carbon 1 to carbon 4 carboxylic acids. Then acetogenesis step takes place with an aim to produce acetic acid. Then methanogenesis, where methane and CO2 is produced. As an engineer, also we need to look for the energy efficiency of these conversions. For example, to produce any organic acids from a glucose, the Gibbs-free energy is around efficiency is around 96%. And if we produce methane, which is around 86%, actually we are losing the efficiency if we go from organic material to the methane production. So when we are dealing with high-strength wastewater, they are highly digestible. And since they are highly digestible, it results acid accumulation within the regular conventional anaerobic digester environment, so which causes process stability, low digestion rates, and require additional effluent treatment. So we wanted to use these imperfection conditions as a new paradigm to produce actually carboxylic acids at higher concentrations to produce them as a platform chemicals. They can be used as is, or they can be used in the formulation of bioproducts as well as biofuels as well. So I would like to share with you our recently published paper when we are using syntropy between anaerobic microorganisms. So if we arrest the methanogenesis, we can produce carboxylate salts. And after separation of purification of these carboxylate salts, it is possible to produce ketones, ethers, aromatics, paraffins from carboxylic acids as well. This is a DOE-funded project. As we all know that U.S. government 2 years ago put a Sustainable Aviation Fuel Grant Challenge to meet the 35 billion gallons of sustainable aviation fuel per year to meet 100% aviation fuel demand to fully decarbonize the aviation sector by 2050. Since Argonne is owned by Department of Energy and operated by University of Chicago, all our research activities align with the Department of Energy's mission. So in order to produce sustainable aviation fuel, we really need to have a low carbon intensity feedstock, as well as to reduce the cost of the sustainable aviation fuel, we need to also low cost feedstock. In that case, high strength wastewater treatment provides a great opportunity. So our aim was to enhance the volatile fatty acid production via new innovative processes, and also explore the downstream acidification and purification via systematic process evaluation. Because when we look at the sustainable aviation fuel, ketonization, aldol condensation, as well as hydrodeoxygenation steps, they are very well known by chemical industry. But what is not known that how we can produce organic acids efficiently, cost effectively, and sustainability. That was our objectives. Traditionally, low volatile fatty acid, as I said, causes process instability issues. We call it sour. Digester become sour because of the acetic acid production or butyric acid production or propionic acid. So we wanted to use these imperfection conditions as a case for us to increase their titer, yield, as well as productivity. So we first started with tailoring the microbial consortia. For that one, we used marine microbes. We collected saline beach sediments. We used the microbes coming from yogurt, kefir, or cheese samples, as well as we used the pure acid producer strains. We expose them to the acid shock as well as heat treatment. We then aim to generate a new microbial consortia. They are highly resilient and robust that can provide us high salt toxicity as well as high volatile fatty acid titer, yield, and productivity. So since we have been developing a new paradigm for resource recovery instead of thinking about the water treatment, so we have to develop a new process with high treatment efficiency, as well as it's going to help us to valorize these low-value organic waste streams that can help us to produce high-value products with low carbon footprint. The most important is that it's going to give us the most resource recovery as well as nutrient recovery from high-strength wastewater. So we started our experiments at a small scale, 0.5 liter anaerobic digester, and we look for what will be the best operating envelope when it comes to these new operations, and we tested temperature, feedstock composition, their concentration, as well as pH, and the microbial consortia. What will be the best microbial consortia that is going to give us the highest acid production? We simulated those experiments in the lab. We then aim to simulate the conventional anaerobic digester operations at wastewater treatment plant. So we took two temperature as an operating temperature for those experiments. Mesophilic, which is around 40 C, and the other one is thermophilic digester operations at 55 C. So based upon the test results, we saw that 40 C is going to provide better substrate degradation or wastewater conversion, as well as acid production. When we check the impact of pH on the digester performance, we saw that if we run the digester at pH 5, we are getting only one product, which is lactic acid. But if we run the digesters at pH 6 and 7, we saw that there is a two-step conversion. All complex molecules first converted to the lactic acid, then to the short-chain volatile fatty acid. And we also conducted metagenomic analysis. It is very important because we need to know what are the key players in highly mixed and diverse consortia. So we found out that Bacillus, Streptococcus, and Enterococcus family microbes are the key players when it comes to the conversion of high-strength wastewater to the high-value products. And we try to understand the link between the wastewater characteristics, operation time, how it is going to impact, how we can optimize them so it can help us to scale up the process to next step, which is 14-liter digesters. As I mentioned before, also we learn how to direct the digester operations through a biorefinery operations. If I set up the pH 5, my targeted product will be lactic acid. But if I want to produce butyric acid or lactic acid, in that case, I have to play with the pH as well as residence time. So those small scale experiments provided the guidance for us to conduct next step of 14-meter digester operations. And we look for many different parameters that they are very important for the next scale up experiments. So we look for the organic loading rates, we look for the retention time, we look for, again, feedstock composition, what are the feed and harvest frequency should be. Based upon those things, we will be able to understand our system response, our system performance in terms of acid titer. We will be able to produce around 42 grams of acid, and 51% of it was butyric acid and 22% was lactic acid. And its productivity is around 15 grams per liter per day. So based upon these optimized conditions, our next step was to scale up the digester operations further in pilot scale. I'm showing a couple of pictures coming from Argonne pilot scale facility. So we run the experiments that optimized conditions determined at 14-meter digester operations at 40C with a COD of 80 grams per liter. It is a lot, I will say. And then at pH 6 and retention time 3 days. So in this slide, I'm trying to kind of compare, is there any decrease when I scale up the process from 14 liters to the 100-gallon digester operations? Actually, at the like 30,000 feet, there is not much differences when it comes to the total carboxylic acid concentration. But when I look at the total volatile fatty acid concentration, I'm seeing a big decrease, about 30% decrease in volatile fatty acid concentration. It tells me that I need to increase the hydraulic retention time further. So it allows the slow grow butyric acid producers time to establish their microbial consortia within the digester system. And also we look for the total acid productivity. I'm not seeing any much change. It was at 14.7 grams per liter per day. It slightly dropped to the 14.3 grams per liter. And when we look at the microbial community analysis, we saw that we are getting the similar microbial consortia that have been established during the pilot scale are same to the microbial consortia at 14-meter digester. This is a good news for us, actually. So based upon those results, we saw that we really need to increase the hydraulic retention time. So that's why we try also submerged membrane reactor operations with an aim to enhance the volatile fatty acid production. When we do that, actually, total volatile fatty acid concentration increased from 22 grams per liter to the 30 grams per liter. And 98% of the acid profile consists of volatile fatty acids. So this was a really great achievement when we switched the reactor configuration from regular anaerobic digester to the submerged membrane reactors. And the substrate conversion was around 72%, which is good. And when we look at the process economics, we saw that product toxicity is also an issue. So to reduce the product toxicity, so we develop an in situ production as well as separation process by using Argonne's electrodeionization patented technology. When we use electrodeionization technology along with the digester, what we saw that actually we were getting better total carboxylic acid production. It was before around 30 grams. By using this in situ production and separation integration, we will be able to increase the acid titer to 115 grams per liter, which is great. And also test results shows that when we integrate the separation and purification to the digester operations, we increase the acid productivity by 36%. And also when we run this unit, we also saw that substrate conversion increased from 72% to 78%. Is about 1.1 fold increase. So in summary, it was a really kind of a great learning experience for us that we really need to also look for the different anaerobic digester configurations to increase the acid productivity as well as titer. So when it comes to the process evaluation, we really need to model the anaerobic digester operations, as well as this modeling is also helping us to design and model individual unit operations based on the, of course, experimental data. By using Aspen Plus and Simpro, we will be able to determine the size as well as the cost of those equipment. It allows us to conduct techno-economic assessment analysis, and also we will be able to calculate the minimum fuel selling price of the sustainable aviation fuel if we use the high-strength wastewater. And the outcomes of the techno-economic analysis was fed to the Argonne's grid model to conduct the life cycle analysis of these new processes. And the integration of this data analysis and modeling is very crucial for the experimental team because it allows us to determine what will be the pinch points to reduce the cost as well as to reduce the greenhouse gas emissions from this new bioprocess. So when we are conducting any techno-economic and life cycle analysis, we really need to determine the system boundary of wastewater. Since this is a new wastewater treatment paradigm, we have to put all required process operations, and then we need to develop scenarios. We developed 3 scenarios. As I mentioned, separation and purification is important because separation and purification can take up to 70% of the total acid production cost. So we focus on cation exchange resin for volatile fatty acid acidification, as well as anion exchange resins, and also recycling of sodium hydroxide, which is one of the important GHG pinch point for us to reduce the GHG emissions from digester operations. We really need to reduce the sodium hydroxide. And we also look for if I produce volatile fatty acid, what will be its application when it comes to the sustainable aviation fuel production. So we determine the required processes such as ketonization, aldol condensation, ionization purification, hydrodeoxygenation, and what are the required unit operations, unit processes, and what will be their operating conditions. So we determine them either from the published literature or using the American Petroleum Institute guidelines when it comes to the operation of those processes. So we conducted techno-economic analysis producing volatile fatty acid from wastewater, using this volatile fatty acid to produce the sustainable aviation fuel. And we conducted those analyses for different wastewater generation. So we started with the 100 metric ton per day to the going up to the 1100 metric ton per day. We then aim to simulate small cheese and beer production, brewery operations in the US, as well as highest operations in the US. So our techno-economic analysis results shows that we will be able to produce volatile fatty acids with a price tag comparable to the current price of the volatile fatty acid produced from fossil-based feedstock. And when we use the sodium hydroxide stream and recycle back to the system, we saw that there is a 36.4% decrease when it comes to the price of the volatile fatty acid production. So we also calculate what will be the minimum selling price of sustainable aviation fuel. Currently, it was determined that it should be around 7.6 per gallon gasoline equivalent. And with these three different scenarios, actually, we exceeded those expectations. And our third scenario actually giving $4.64 of fuel price for us. So when we are conducting any techno-economic analysis, we have to also conduct sensitivity analysis, considering the all cost drivers that is going to be part of the cost calculations. So we look for the changes in total capital cost, how it is going to impact, or how the electricity price is going to impact, or how the water treatment is going to impact the total price of the volatile fatty acid. Or when it comes to the sustainable aviation fuel, for example, we look for the toluene price, which is mostly used for production of sustainable aviation fuel. So based upon those sensitivity analysis, we will be able to determine the impact of each parameter on the total selling price of the volatile fatty acid as well as sustainable aviation fuel. And the outcomes of this techno-economic analysis were used to conduct the life cycle analysis. I'm sharing with you the life cycle analysis results. Currently, fossil fuel jet has a 85 grams CO2 per megajoule sustainable aviation fuel. So with this new approach, we will be able to produce, especially with scenario 3, 3x less than the current fossil jet greenhouse gas emissions. So this is a really great news for us. So we also look for the water consumption with respect to fossil fuel jet production. Unfortunately, the second scenario is not matching up the current one, but the third scenario is giving us negative values that shows that we are also conserving the water with this new approach as well. So in summary, I would like to share with you that we develop and scale up a novel process from 0.5 liter to 375 liter within 3 years to valorize the high-strength wastewater through carboxylate platform. And we develop a robust and resilient microbial consortia, which is very important for any bio-based process operations. And we also experimentally determine the links between wastewater characteristics, microbial community structure, as well as digester operations. And experimental results shows that this new anaerobic digestion technology has the potential for large-scale application, especially transforming low or negative value high-strength wastewater to a high-value products. And currently, we are scaling up that technology from TRL level 5 to further. So with that, I would like to acknowledge Department of Energy, Bioenergy Technology Office for providing us funding to conduct this research. And I will be happy to answer your question. Thank you.
Great talk, Meltem. That was really interesting. I'm curious about the engineering of the consortia, and I'm wondering, so I think you mentioned you used 3 different sources of inocula, right? And I'm wondering, which I thought was really interesting, have you looked at sort of the inoculum impact if you were to use just, anaerobic digester biomass directly? Is there a big influence on performance, or how important is it to use those 3 elements? Does that make sense?
So yes, we can use also inocula coming from sludge.
Yeah.
But when we are using sludge, it is a biosecurity level 2 microbes. So,
Got it. Okay.
But when you are using microbes coming from nature, there is no restriction. So also it is easy to operate. So we need to think that aspects as well. When it comes to the acid production, we really need acid producing microbes. That is the most important things. But when we use the sludge, also we are missing one thing. When we are dealing with the high concentrations of acid, there is a product toxicity. And we need to have consortia that can tolerate this high acid toxicity. And the third thing, which is very important, during the operation of anaerobic digester, we always add alkaline materials. So when you add these alkaline materials at high concentrations, actually at the end of the day, we are accumulating salts within the digester environment. So you need to have microbial consortium that can tolerate also high concentrations of salts as well. There are a couple of tricks that we need to kind of solve it. So that's why we went, for example, I was in American Chemical Society conference in New Orleans. I went to the ocean and collect the soil samples close by the beach because there is a grassy area. So you can find that microbial consortia, they are tolerating salty water, salt, which is found in the sand samples as well. So that's why they are specifically picked to establish that consortium.
Very interesting.
Yeah,
Thank you.
many reasons, I would say.
So we have time for maybe one short question.
Hi, great talk, Meltem. Can you speak at all to the interest from the aviation industry for adopting these biofuels, and if there are any technical challenges on that end? Like, do they have to adapt any of the existing infrastructure in the planes to utilize biofuels?
Very nice question. So currently there are 9 ASTM standards approved, ASTM certified 9 pathways available for producing sustainable aviation fuel. So these are the next generation aviation fuel pipeline, I would say. So it depends on the scale up. So currently we scale up our technology from TRL level 2, technology readiness level 2 to 5 within 3 years. And next 3 years, we are really looking for TRL level 7 or 8. So industry can easily adopt. So scalability is very important, as well as meeting the ASTM standards are very important, because the fuel is not going to be used ground transportation, it is going to be used in air. So they have a really stringent certification process. But if you are looking for current publications coming from many national laboratories, we are right now specifically focusing on this new pathway using arrested metagenesis technology to valorize food waste, to valorize high-strength wastewater, so that volatile fatty acids can be used as a new low carbon intensity feedstock to produce the sustainable aviation fuel. We have Fulcrum located south side of Chicago. Actually, it is located in North Indiana. So they are using, for example, garbage, right? They are converting to the sustainable aviation fuel. That is one pathway. It is already approved. But also to meet the 35 billion gallons of sustainable aviation fuel by 2050, we don't have much time. So we have to develop new technology pipelines are going to be ready within 5 or 10 years. So that's why national labs are working in that area. I don't know if I answered your question.
I think that was a great answer. Thank you very much for the very interesting talk with, I would say, unexpected pathways for reuse.
Yes.
Thank you. So next speaker will be Brian Chaplin. And presuming that's all going to go up, introduce Brian. Brian Chaplin is a professor of chemical engineering from UIC. He's done a lot of work on different types of electrochemical technologies for various water treatment processes. So using electricity, generate chemical reactions, or in combination with chemical reactions for a wide range of applications, including things like anti-fouling coatings, getting rid of bacteria from membrane surfaces, which is a major challenge, and for a wide variety of contaminant removal processes. So looking good.
Sounds great. Yeah. Your intro is great. I don't know about the AV issues.
Yeah. So today he's going to talk about one of these interesting applications, electrochemistry for PFAS removal, which of course is something of concern to many people here today.
Thank you, Aaron. Okay, I can probably get started here. So yeah, it's a pleasure to be here. Thanks for everyone for joining today. And I'm going to be talking, as Aaron said, about electrochemical destruction of PFAS. If you don't know that name, you've probably heard of the term forever chemicals, which is more of the popular press. So we have developed a technology that we call reactive electrochemical membranes, and we've been researching electrochemical destruction of PFAS for several years now. Okay, so to set the stage here, PFAS, or forever chemicals. I'm going to be using a lot of acronyms here. So if you're in the area, be no problem. If you're not, you may be a little confused. But do I have a laser here too? Okay. So I'm just showing some general structures. So I'll be giving a lot of abbreviations. The PF is perfluorinated, just meaning we have carbon chains without hydrogens, but instead fluorines saturating them. And two main categories are going to be the sulfonates with the sulfonate head group, and octanoics or carboxyl acids with a carboxyl group. So these will be the abbreviations I'll be using. And a lot of times this letter will change, which is just the length of the carbon chain. Okay, so PFAS are present in lots of industrial products. And main sources of PFAS to the environment can come from industries. These are more regulated now, so there's not a lot of direct discharge. But a lot of the wastewater from industries that utilize these chemicals are going to wastewater treatment plants. A lot of the consumer products that we use that contain PFAS, at the end of the life, they end up in the landfill. And so what really happens is there's a large amount of these chemicals are going to wastewater treatment plants. Wastewater treatment plants are not designed to remove these chemicals. They don't necessarily pass through to the water at great concentrations because of their hydrophilic properties. So there is some discharge into local streams, but they accumulate a lot in the biosolids. And that's a big problem because biosolids are typically reused in agriculture and other beneficial reuse practices. And so the fact that these are now going to be classified, at least some of these, as Superfund chemicals, it brings a huge concern about what do we do with all this biosolids. Not just for the beneficial use, but what do we do with all this mass? So it presents a lot of problems that we'll be trying to solve in the decades to come. Other sources are things like firefighting foams, and these are really relevant to the Department of Defense sites, and a lot of the funding for PFAS research has traditionally been from the DoD to remediate these from groundwater. So a little timeline here. So PFAS was invented accidentally in the 30s, 1938. It was actually a refrigerated, looking at refrigerants, and they actually had a polymerization reaction inside of a pressurized vessel and discovered Teflon. And that's where the story begins. And so they were first used in the Manhattan Project, so here in Chicago, for the nuclear bomb. And then over the decades, were incorporated into more products. Around in the 2000s, where analytical chemistry became much more sensitive, these compounds were detected worldwide. And then within the last few years, really, there's been a lot of activity to actually regulate it. So I'll go through with the timelines quickly here. In 2001, the House passed the PFAS Action Act, tasked the EPA to start to regulate PFAS. From there, they went through a process of developing health regulatory limits. And ultimately, just last month, they have federally enforceable standards for many of these compounds. So PFOA, which is a common one, 4 nanograms per liter. PFOS, 4 nanograms per liter. Down here, PFNA, 10 nanograms. PFHex-S and GenX, both 10 nanograms per liter. So to put this concentration in context, if you had a grain of salt, small grain of salt, that would be about 1 milligram. So we're talking about orders of magnitude smaller than that. So the amount that is in a liter of water, you can basically not even measure or see. So it presents a very big challenge to the remediation of these chemicals from water. So I'm going to get into the remediation technologies. This is what we're focused on. Currently, what's being used is mainly separation technologies. This might be activated carbon, ion exchange, reverse osmosis. They're fairly effective for removing these chemicals from water. But the problem is, especially now that these are being regulated and are hazardous waste, we need to have methods to destroy them. So our research is focused on destruction. There's various groups looking at different methods that show promise. I've listed some of them here: UV-based treatments, hydrothermal alkaline hydrolysis, and what we're focused on, as well as plasma treatment, what we're focused on is electrochemical oxidation. So a little background on how these chemicals can be destroyed by electrochemical oxidation. We think of this as having two different oxidation mechanisms. There's, in general with electrochemical oxidation, there's indirect oxidation, where water can react on an anode surface, produce these very reactive hydroxyl radicals that then react with other compounds. Hydroxyl radicals are not, PFAS are not reactive with hydroxyl radicals. So a lot of these advanced oxidation processes that have been used in water treatment do not remove these chemicals. The other mechanism for oxidation at an electrode surface is direct oxidation, and this mechanism can actually lead to destruction of PFAS. So the compound can approach the surface, transfer an electron into the anode, producing a radical species, and then a combination of these hydroxyl radicals as well as these direct oxidation reactions can ultimately lead to mineralization of these compounds. So if we have PFOS, we can end up with sulfate, fluoride, and CO2, which are harmless end products. There is a lot of concern with what happens once we remove some of these compounds, the parent compounds, because traditionally they're forming shorter chain compounds that are still toxic. So eventually, to alleviate concerns about toxicity of products, we really need to go to the mineralization, which is difficult and requires lots of energy. The electrodes that we've been using in our research are known as magnetic phases of titanium dioxide, and basically this is a fancy word just for suboxides of TiO2. So what we do is we take TiO2 and we heat it up at a high temperature in a reductive environment, and it brings oxygen out of TiO2. And that process makes it electrically conductive. And we have a graph here showing that if we get to the phase of Ti407, which is TiO 1.75, that has the maximum conductivity. We've also have other studies that show that produces the highest yield of hydroxyl radicals, which is good in general for electrochemical water treatment. Also, if we compare it to the state-of-the-art oxidation electrodes, which are boron-doped diamond, they're about 10,000 times cheaper on a surface area basis. So it's considerably cheaper than state-of-the-art electrodes. One advance that we've done, which is a very simple concept, but it's very effective, is the redesign of the electrode structure. So typically, electrochemical reactors will operate like this, where we have two flat plate electrodes and we flow water in between them. What happens in this scenario is you get a very large diffusive boundary layer shown here. And so the contaminants have to diffuse maybe 100 microns to get to the surface. And so even if you try to increase the surface area by putting features of roughness on the electrode, those are usually very small compared to this length scale. So they get averaged out in this diffusive field, and they don't really take part in the reaction. What we've done is made porous electrodes, shown here, where we can flow the water through the pores. Nominally, they have about maybe a 1 micron pore radius. And so that shrinks down this length scale for diffusion. We have 100 microns here. We have the pore radius of 1 micron or less. So in that scenario, we can actually put features of roughness that are on the same order of magnitude as the diffusive length scale, and they can take place in the reaction. So we can get high removals with just a single pass of flowing it once through these porous electrodes because of the very high surface area, the fast mass transfer. So we have a technology that we're calling reactive electrochemical membranes. We have a patent on this, and this is showing some of these tubular membranes. We start with TiO2, we reduce it to Ti407, conductivity increases by several orders of magnitude. And you can think of this, if we operate this like a typical membrane, it has the features of separation, but also has the features of being a reactive surface. So we can think of this as this high surface area can be a collection of these microelectrodes where we can have all the internal surface area in these pores take place in the reaction. So here's our experimental setup. I'll go through this very quickly. Our first set of experiments I'll show today is done in what we call 100% recycle. So we have a feed tank here. We flow the water inside of our membrane. We pressurize that, which causes water to flow through the pores of the membrane. And in these experiments, we're doing 100% recycle, just meaning we're sending the permeate back to the feed. And we're looking at how the concentration in the feed tank will change with time. Because we're operating in this fashion, we do a pretty high flow rate. This is membrane units. So this is liters per meter squared per hour. And we'll look at a few different current densities. So my first example here is just looking at a groundwater sample. So this is from a naval base, and this is part of a DoD project that we're working on. So this is the general groundwater composition, nothing too exotic here, typical ions that you would find in groundwater. And this is the different PFAS compounds. You can see the alphabet soup here, but kind of the overall message here is we have about 12,000 nanograms per liter of PFAS in that groundwater, which is a high level for PFAS, but also if we think about total mass, that is still a fairly small mass of chemicals. So just to summarize our initial experiments here, we looked at different current densities. I'm going to just focus on the highest current density. So black is where we get fairly good removal. Green is somewhere in the middle. And the negative removals actually mean that we're accumulating these compounds because they're products of other things that are present in the groundwater. So we can see overall, we do a decent job on this, 84% PFAS removal. We have good removal of PFOS, PFOA, which are now the Superfund chemicals. And then some of these shorter chain compounds, like penta, this is 5 carbons, buto, which is 4 carbons. Some of these shorter compounds we actually see accumulate. Okay, and so if you're into the details of these oxidation mechanisms, that might seem a little strange because usually if you take a parent compound like PFOA or PFOS, it's going to degrade to form carboxylates. So the fact that we have these sulfonate compounds accumulating is likely related to some of these precursors that we have in solution. So these are different structures that I'm showing that I showed early on. And what we think is going on here is we're cleaving this sulfur nitrogen bond in these cases. So that is actually producing some of these shorter chain compounds. So this is our initial result with groundwater. And what we've kind of determined from this is, although the electrode material that we're using can degrade these compounds, it's doing it too slow. So we need to be able to speed up this reaction. So where we go from there is to put a catalyst on the surface of our electrode. And we're using a bismuth oxide, tin oxide catalyst that I'll just abbreviate BTO. And this is just showing some images of the porous structure. This would be our substrate of that Magnelli phase Ti407. This is once we electrodeposit our catalyst on that surface. This is just showing the current profile that we use for electrodeposition. SEM EDS characterization is important so we can see, do we deposit that catalyst uniformly on our substrate? So this is the surface, bismuth, tin, both look uniformly distributed. And if we look at the cross section, so this is the thickness of our electrode here, we see a relatively uniform distribution of these metals. So that's important so that we can have reaction throughout the whole depth of this porous electrode. When we started work here, we did a slightly different reactor here. So we're looking at just these pellets in order to just save on the mass of chemicals used. And here, instead of doing 100% recycle, we're looking at a single pass, meaning how much removal can we get with just passing through the electrode once? Because ultimately, that's what we're going to want to do in practice. And so our first results, we just are looking at PFOA oxidation. And this is a surrogate just to see, okay, is this technology effective? And I'll go over the experimental conditions here. We have a high concentration of PFOA here, and much higher than what we saw in the groundwater. And the reason for this is most technology treatment trains are thinking, okay, destroying the chemicals directly in the groundwater is not energy efficient. So first you want to concentrate them by some means. That could be by a membrane, it could be on a sorbent, and then take that concentrated solution and then do some kind of destructive method. That's going to be the most energy efficient and the most affordable. So we start with a high concentration. We use an inert electrolyte, and our residence time is 13 seconds. So everything I'm showing here is just 13 seconds of reaction time. How much removal do we get? So as we increase our potential, we can see that our normalized removal is increasing, and we get about a little bit over 90% removal at our highest potential that we tested. We also are tracking the products, because that's very important, because these are toxic. So we look at our fluoride yield, which is shown here. And this is our total fluorine balance, which also includes these shorter chain compounds. And in these cases, we have about 70 to 80% yield. So that's a concern, because we want to close the mass balance, because all these chemicals products can potentially be toxic. And what we see is just a chain shortening. So hep to hex, 7, 6, 5, 4 carbon chain. So this is typically showing that we're producing a total of about 10% as these shorter chain carbons, which these may be regulated at some point as well. So those are concerns. When we look at the different fluxes, the main reason for doing this is just increasing the residence time. So I'm just going to focus on our lowest flux, which gives us our highest residence time here. So a single pass would take about 54 seconds. We have 98% PFOA removal in just that amount of time, 92% defluorination. And if we do our mass balance in that case, looking at the shorter chain compounds, we have almost within uncertainty 100% mass balance. So what that's telling us is that when we have these faster fluxes, shorter residence times, we're forming products that we're not detecting by LCMS, because we're not necessarily looking for everything. We have targeted analysis. But what it's telling us is if we give it longer reaction time, we are able to degrade all of those compounds. And this is a scenario where we have some of these shorter chains, right, that are still a concern. We could possibly run that through an absorbent at the post end of this. But we are tracking 100% of that mass, so we know what's being formed. This is very important. Okay, if we look at the effect of carbon chain length, that's important, because what we saw in this prior slide is that we're starting to form successively shorter carbon chains, right? So we have to look, okay, so the reactivity of PFOA may be something, but when the chain shortens, how does that reactivity change? And this is all done at a very short residence time. So we're actually repeating these at longer residence times. But for the short residence time, we see PFOA is removed the fastest. PF-HEP-A is a bit slower. And then we're not seeing any removal of these shorter chain compounds. So we have other experiments where we've increased that residence time and we do see removal. But the kinetics in general, as the chain gets shorter, the kinetics slow down. So if we start to, in the future, if these shorter chains become regulated, they are going to ultimately dictate what kind of system we have to employ for treatment here. The total fluorine balance is a little bit higher for HEP-A versus PFOA. And if we look at this total balance, we're still in this, 70, 80, 90%. So there are some compounds that form under these fast residence times that we're not detecting, but we did show in the prior experiment that we could oxidize those. Okay, this is just showing the short chain compounds for these two experiments when we start with PFOA and we start with PF-HEP-A. And the general trend we're seeing is we get about 10 to 12% of these shorter chain compounds. So if you're thinking about the mechanism for this, traditionally what was talked about was, so if you love chemistry, this is great. If not, look at your phone. But the traditional mechanism that was proposed was whatever compound you start with, you're just cleaving one CF2 group. So if you start with PFOA, then you'll go to HEP-A, and you'll keep going down the chain. But the results I showed you would say that can't be possible, right? Because we saw the kinetics almost go to zero here. So if this was the case, then we would just start to accumulate, for example, hexa. So our experiment should show that in this resonance time, it all goes to hexa and stops. So the initial proposed mechanisms cannot be entirely correct. There was a very good paper from the Crittenden group at Georgia Tech that proposed an alternative mechanism. So I'll just summarize it here. Is our blue pathway here, without talking about the details, this is saying that we have sequential chain shortening. The red pathway is the traditional one, the first one that was proposed. This was the initial one that was proposed for chain shortening. This is an alternative pathway that does not have chain shortening. It goes through this alcohol intermediate and basically just forms a radical that likely absorbs the surface of the electrode and then further reacts. So there seems to be a small amount, about 10% of the yield is going in this direction, producing these shorter chain compounds. And roughly 90% is going through this one, which is good in our case because it's forming these radicals, absorbed to the electrode, further react, and allows us to achieve close to complete mineralization. Okay, so I think I am done. So just to summarize, what we saw in our initial experiments that I shared was that the groundwater, we were able to do about 85% removal of these compounds in this full recycle mode, but we did notice that these kinetics are not sufficient for what we would like. So we are exploring this tin bismuth oxide catalyst. I didn't show the controls, but we were getting about 10 times faster kinetics than just using this substrate by itself. And then what I just talked about at the end is that this product yield, as well as our reaction kinetic studies, indicate that the traditional mechanism is not what's happening for electrochemical oxidation. And as we move forward with this work, we're really focused on catalyst stability and treating these concentrated streams. The problem that we have is that the carbon-fluorine bond is so strong, and you saw the very high potentials I have to get to remove these compounds, that you can imagine that everything else is also destroyed. So we've had, we have to move to expensive current collectors and really focus on our ability to immobilize this catalyst under these very, very high anotic conditions. So that's work that's in progress. So I'd like to acknowledge the group that's shown here. Funding from this work, the initial funding was provided from NSF for the development of our reactive electrochemical membranes, and then all the PFAS work that I shared was funded by a CERTA project. So thanks for your attention. I'd be happy to answer any questions.
So we have at least 5 minutes. Question, maybe up to 10 minutes of the time. You come right in and ask a question.
Good to see you. Such a lovely talk. I think it's a great idea to be able to oxidize and get rid of it. My question is how, I'm new to this field, so if you could help quickly as to what are the different analytical methods for detecting not just PFAS, but the subvariants, and is there an opportunity for innovation there in terms of timing and sensitivity? Can you shed some light on that?
Yeah, good question. Yeah, the state of the art is LC-MS. And so that's obviously an expensive, complex method. So there is a lot of interest in developing, lower cost methods. We have some work on sensor development for this. It becomes very difficult if you want to distinguish between the different compounds. But having some kind of cheap, maybe diagnostic method, like a sensor to say, okay, we do have PFAS here. Now you can spend the exorbitant amount of money for LC-MS instead of, just, screening everything with the expensive method. There could be a lot of opportunities.
Do these techniques have the sensitivity and the range? And especially the contaminants because the other microplastics mixed in and so
yeah, nothing that I've seen, right? A lot of this is in development. I've seen lots of papers on sensors, but practicality, I don't think anything is very far along at this point.
That's a good area to.
Good area to work in though, yeah.
So is there a question over here or Meltem? I think I missed somebody's hand.
Thank you so much for this great work. I was wondering if you conducted any preliminary techno-economic assessment analysis to determine what will be the dollar per gallon of that water treatment.
Yeah, I mean, that's work that we need to do in a month for our final project report for this project. We've started some preliminary LCA, and really, I mean, it's kind of the results are kind of obvious. Is that the concentrating it first makes all the difference in terms of the life cycle impacts as well as the energy consumption. So if you can concentrate by a factor of 1,000, you might only need to add one additional stage to your treatment process. But you have that, treating groundwater basically is 1,000 times more environmental impact. We haven't done the cost yet. 1,000 times more environmental impacts versus concentrating by a factor of 1,000, because you might have to double your treatment technology size but you're treating 1,000 times more mass of these chemicals. Yeah. So hopefully we'll have those numbers for you soon though.
No, it was just easier.
Breaking protocol.
So first of all, it's amazing work that you're doing and
Thank you.
daunting. So PFAS has gotten to be an everywhere chemical as well as a forever chemical. So with microplastics and climate change, the whole thing has gotten worse. It's in rainwater. It accumulates everywhere. So in coming up with these solutions on how to neutralize it in a realistic way, what kind of time frame?
Time frame for cleanup?
Yeah, like to make this problem not happen. So this problem didn't exist before the 1930s. Less than 100 years later, we have a global disaster.
Well, yeah.
Do you think it's going to take another 25 years to kind of make this go away? Or, I mean, this is a really tough, knotty problem.
Yeah, I mean, it's a great question. I can't really, I can talk generally about that.
Yeah.
But I mean, I think what needs to be done is regulating the use of these chemicals, because if we keep putting them in the environment, right, it's going to be difficult.
There's a hole in the bucket.
Exactly. So, and there seems to be some, to be honest, I don't think water is our biggest problem in terms of exposure routes. Cosmetics, they're in a lot of cosmetics, they're in sunscreen, like, and what industry typically does, maybe, hopefully not this time, is, right, okay, PFOA, you can't use PFOA. Okay, then we'll just make something that's a little different than PFOA, just as toxic. That's what they did with BPA, right? So these games are not being played. And there's actually federal regulation in food, like food packaging, right? Like that's going to be probably a bigger source than drinking at 10 nanograms per liter for your lifetime, definitely. So trying to find the primary sources where we're exposed to, regulating them, that's going to be huge. The whole cleanup of what we have is going to be huge, because it's like PCBs, that was decades, right? So I can't even really fathom how many decades this will be going on. But it'll be significant. And then the fact that now it's going to be hazardous waste. Like, I mean, and maybe like George can comment on that. What if biosolids are all now hazardous waste? What do we do? Yeah, it's a huge problem. I have no idea. I have no idea how to manage that in an economic fashion, right? It's going to be difficult.
So we're a bit short on time, so 2 more questions and try to keep them direct.
All right, I'll try to be quick, but there's a reason we call these forever chemicals. So when will it be solved? I don't know. But I think we're going to be treating our water forever to deal with the contamination we've created. So my question is, we have this progression of breaking down these compounds into smaller, shorter chains.
Mm-hmm.
Do we need to look at anode materials, cathode materials that are targeting different chain lengths, different functional groups? Like, is this going to need a bunch of extra stuff if we care more about other compounds besides PFOA?
Yeah, I think what happens in that, because we were doing the studies, we didn't put them in this one, that we can degrade everything, no matter how short the chain length. It might just take a longer residence time. So I think it's going to be one of these things where if you start to regulate these shorter ones, you might have to add an additional. I'm thinking of this as a stage system, like a membrane, right? You run through one reactor, you might get a log removal, and you might have to send it through another reactor. And then I think when you get down to a low level, it doesn't matter. It's not meaningful to treat them electrochemically. You might want to absorb them again. But in terms of functional, I mean, you're kind of going to the thing of, can we functionalize the electrodes to be very selective for short chains versus long chains? We've tried to do that quite a bit, or at least in a general sense. What happens is if you use any kind of organic type of absorbent to try to functionalize, it goes up in smoke, CO2, because they're not as stable, right? We're trying to break carbon-fluorine bonds. So if we have carbon-carbon bonds, carbon-oxygen, you basically degrade those sorbent that are supposed to help with selectivity. There might be a little more, there's more room on the reductive side, doing electrochemical reduction in terms of functionalizing, but electrochemical reduction, the rates are just very, very low. It doesn't seem to be promising at this point, but that's why we're all investing time and money into research.
Okay, so I was gonna say that if you wanna get rid of forever chemicals from your body, you should try to donate your blood as much as possible. Because that does get rid of it.
So, are you doing a service to who you're donating it to, though? Yeah, we actually kind of a little bit of a side on that is all my students got very concerned, so I had to pay for all of them to have I almost said drug tests. Well, I should do that, but blood tests.
So,
And
well,
they're all within the normal limits. So I should get back to work in the lab.
well, I'll support the blood donation argument, but not for necessarily this, but as a good beneficial reuse.
Right, I think we'll get started in session 2 of the symposium. Again, my name is George Wells. I'm an associate professor of environmental engineering at Northwestern. I have the pleasure of introducing a visitor from a long ways away. Hadas Ranaan Kiperwas is in from Israel, where she is a lead researcher at Mekorot, the Israeli National Water Company, I think it's called. Yes, exactly. Leading fascinating work on emerging and advanced technologies for water and wastewater treatment. Hadas has an undergraduate degree from Ben Gurion University. She also did her PhD in geochemistry and hydrology at Duke University. And I learned last night she spent some time with the US EPA.
Very short time.
I believe.
Yeah.
A short time, exactly. So a range of very relevant experience. So Hadas, really looking forward to your talk. I'll turn the floor over to you.
You can hear me, right? Okay. So I'm going to be talking to you a little bit about reuse in Israel, what we've been doing so far and what we're planning for the future. A little bit about Mekorot, which is Israel's national water company. We handle thousands of installations of various types. We are the largest supply of water in the country, both potable and other types of water. And one of the main reasons why I'm here is because we also deal with wastewater purification, treatment, and reuse. Mekorot supplies many different types of water. We have a very interesting, complex, and to some extent unique system. We supply both desalinated water, which George mentioned before, groundwater, surface water, effluent, and also brackish water, so brackish groundwater, which we desalinate and currently use for agriculture, but in the future might use for potable uses. And those water are supplied for industrial uses, domestic, and agriculture, which is what we're going to focus on. So this is a different version of the graph that George showed you earlier about water sources for agriculture in Israel. And what you can see is that the amount of potable water we're allocating for agriculture has been in a constant decrease. The amount of brackish water we use for agriculture is pretty constant, but the amount of effluent we're using for agriculture is gradually increasing. I think today we're closer to 50% with respect to like the amount, the percentage of reused water that are a source for agriculture. So that's what I'm going to focus on reused water as a water source for agriculture. So Israel is a very complicated and has a very complicated environment, and that's why water reuse has been practiced for so many years. I mean, we started reuse in the 80s. So it's been north of 40 years that we've been doing that quite extensively. And the main driver was just sheer necessity, the lack of water, a huge discrepancy between where water falls and where water is needed, between where water falls and where agriculture is practiced. And we have the advantage of water being managed as a national resource that allows us to make large-scale decisions and build national projects to convey water from one end of the country to the other end of the country. But on the other hand, you have to keep in mind that the size of Israel is 1/3 the size of Lake Erie. So it's a very small country, which also makes it a lot more feasible than in many other places. So a little bit about what we've been doing during the past 40 years. So we have many wastewater treatment facilities around the country, and we've been practicing reuse from all of them. But the most interesting one probably is at the Chaplin, which is the wastewater treatment facility servicing the larger Tel Aviv area. It services some around 2.2 million people equivalent. And what's happening at Chaplin for about 40 years now is that the sanitary wastewater of the greater Tel Aviv area goes into the wastewater treatment facility. It's now being enhanced and improved, but generally speaking, it's a activated sludge, typical like wastewater treatment facility producing secondary effluent. And Mekorot has been operating it for decades now. But then once the secondary effluent is produced, that's when it becomes more interesting. How do I point? Top one? Okay. So once the secondary effluent is produced, we then go through a process that's called SAT. That's soil aquifer treatment. I'll elaborate a little bit about it in a second. And then once the water is reproduced from the SAT, it goes through a dedicated line to the south of the country for irrigation. And the type of irrigation that's practiced for these particular water, reclaimed water, is basically the same as you would with potable water. It's without any restrictions, even regulation-wise. The type of permits you need to apply for irrigation with these water is the same as you would for potable water. You'll see the water quality shortly, and you'll probably understand why. So this is the SAT process, the soil aquifer treatment. Basically, we take secondary effluent from the Chaplin, and we infiltrate it in dedicated infiltration basins in the sandstone aquifer that we have along the coast of Israel. So it's a very loose sandstone aquifer, and like the topsoil is just loose sand. So it provides a really good natural filtration mechanism that also hosts a lot of bacteria that can break apart some of the organic matter that comes in with the effluent. We infiltrate the water through the soil, it goes to the aquifer, and then it's produced in recovery wells. And once it's produced, we call it reclaimed water. And it's a very unique type of water. You can see here the similarity of the reclaimed water to what you would expect from potable water. Has very low TSS, BOD, TOC, very low nitrogen, and like with respect to bacteria, also the same constant, the lack of bacteria that you would expect from a potable water source. It's actually so unique that it's not even officially defined in our regulations. It's just that's the water quality that's been produced for that water source for the past 40 years or so. And for that reason, our regulations allow to use it without restrictions for irrigation, even for leafy greens. The challenge becomes that the Chaplin is located in the suburb, like outside of Tel Aviv, a little south of Tel Aviv, but it's all along the coastal Mediterranean. And we have a huge challenge with housing in Israel. Everybody wants to live in the center, and lands are very limited. And some of those infiltration basins are located right where people would really love to live. And it's practically impossible to create new infiltration basins. And the existing ones are at capacity. So, and of course, population keeps growing in the center. So we need more and more solutions to be able to produce more of this type of water, to be able to produce more agriculture, and to treat the growing amount of effluent that's being produced at the Chaplin. And we cannot, as I mentioned, create new infiltration basins. So it's been clear for almost 2 decades now that we have to come up with an alternative solution that can produce the same quality of water but in an engineered technique, or in an engineered way, not a natural-based solution. And the biggest challenge, like the first challenge we had to overcome, was what would be the water quality we would need to meet, because the reclaimed water quality is not defined by regulations. And the plan is to convey whatever water comes out of this engineered solution at the same pipeline with the reclaimed water from the soil aquifer treatment. So our Ministry of Health, who is the one regulating water quality and water uses and says how you can use which type of water, they had to instruct us what type of water they want us to create, or to what level they want us to treat the water, in order for them to agree to call the produced water from whatever engineered process we end up selecting to qualify them as soil aquifer treatment, or SAT equivalent, and allow us to put both types of water in the same pipeline and treat them regulatory-wise the same way. So they didn't give us MCLs. What they did give us is a list of instructions of what they would want that technology to be like. So a lot of the criteria here are borrowed from the California Title 22 guidelines, the log removal requirements, the number of barriers, and the log removal criteria for the different barriers. The 80% removal requirement for trace organics is borrowed from the European regulations for trace organics. And they also wanted us to use technologies that can be adapted as tier 1. So just to clarify some of those terms, when we talk about log removal, we talk about the percentage of whatever contaminant we're talking about, or in this case, viruses and crypto and giardia, so pathogen. So if we're looking at one log removal, and we had, for instance, 10 viruses of a certain type, one log removal will move to one virus. If we had 10 to the 10th of the certain virus, 10 log removal will get us to, again, one virus. So that's the idea behind log removal. And just I think it's an interesting and important concept, because it puts, it makes the engineers, it forces the engineers to interact with regulations. So the log removal is given as a credit. It's not that that we actually have, for instance, 10 logs of, so 10 to the 10th viruses in the effluent that needs to be removed. We actually have 10 to the 3rd that needs to be removed. But we need to have technologies that can, when we sum them up, they get credit for the removal of 10 logs. And that credit is based on systematic research and acknowledgement by regulators, mostly EPA, and also Australia Waterval. They also work with the same system of log removal. So that you have to find technologies that have been accepted by regulators and have been credited a certain log removal credit to be able to use them this way. The other term that I want to explain is tier 1. So there are certain different ways you can adapt the technology for a treatment train. And the difference between the different tiers is how hard you have to work to have the technology accepted and to kind of verify it. Tier 2 and tier 3 are more site specific. They're more specialized. But tier 1 is the kind of simplest way of adapting a technology. You basically, you don't have to do any validation tests on site. Usually it's because there's a proxy online sensing technique you can use that would be a good enough indication of whether or not you had a breach in the efficiency of your technology. And it's also the most conservative one. So you would get the lowest removal credit if you use tier 1. So for instance, I'm going to mention MBR in a minute. Using tier 1, you can get a 1.5 log removal credits for MBR, but in California, they did a tier 3 study and decided to grant it, I think, about 3 credits. So tier 1 is the most conservative one, but also the simplest one to adapt. So one of the requirements was that we only use established technology with successful full-scale installations, and we need to adapt the technologies as tier 1. And of course, the system also has the treatment train which also had to be affordable, had to have minimal environmental impact, and it needs to be delivered through the same system and acknowledged by. These are the terms we had to meet to get acknowledged by the Ministry of Health as SAT equivalent. And this was quite a new approach in Israel for meeting a water quality demand, because usually we work with MCLs, like most everybody else. So this was really a challenge. We had to think long and hard to come up with a treatment train and to decide which of the treatment trains that kind of made it up to the final selection we should actually adapt. We had a national steering committee made of a lot of regulatory bodies, and we visited certain facilities in the U.S. and we talked to Perreault Engineering to get some of their advice. We had an NWRI panel advising us, and we ended up coming up with 3 main treatment trains that made it to the finish line. They all had their own advantages and disadvantages. The main disadvantage of like the immediate suspect when you're talking about effluent treatment for reuse at that high of a level, because basically the level we were asked to treat the water to is what you would call in many parts of the U.S. for the quality for indirect potable reuse, and at least in many places the most acceptable or the best available technology is considered to be UFRO. And the main reason why this was not selected in Israel is because of the brine production, because the brine contains a lot of trace organics, and there is no good solution for the brine from the UFRO system currently. Basically, it's usually being discharged to the Mediterranean, which is something that our Ministry of Environmental Protection does not allow, because of several accords we are part of, and the solutions that can be adapted make the technology so expensive that it's just no longer feasible. So that's why the classic UFRO treatment train was not valid here. We also considered starting with ozonation, back filtration, and then going to a filtration step. But this was not possible either, because we needed some sort of pre-treatment before ozonation to make the ozonation effective and both mostly costly. So this is the treatment train we ended up selecting, which was in the last row there. Low-loaded MBR, ozonation, back filtration, and then UV disinfection. The goal of the system as it all, and also of its different components, is to both improve the quality of the water, get rid of trace organics, and mainly to disinfect and remove pathogens. The reason we're starting with low-loaded MBR, which is not very common, we're actually, I think, the second ones to consider this. It has 2 reasons. First of all, it has to do with the regulatory requirements for ozonation, and we had to reduce turbidity quite significantly, so that ozonation is effective, and it's actually making it fulfilling its role in both trace organics removal, and disinfection. The other reason is that the Shaftan currently is not fully nitrified. So it produces not only nitrate, but also nitrite and ammonia. And nitrite is a huge ozone gasler. And ammonia is a precursor for byproducts. So we had to make sure that before we enter ozonation, we get rid of as much of the nitrite and ammonia as we can, basically reach full nitrification. So that's pretty much why we had to start with an MBR and not with a UF. Another reason is the whole accreditation process and the requirement that we apply technologies that can be applied as a tier 1, so without any need for daily testing and verification. To get removal credit for UF, you have to do daily pressure decay tests, which is, you're talking about a full-scale facility. It adds a lot of complexity to the operation. So it can only be used, so it cannot be used without any daily verification. Whereas a low-loaded MBR or an MBR generally, you don't need to do those daily checks. You can just monitor your turbidity. So that's another reason why we couldn't use UF as the first step here. So you can see below the water quality goals we had to meet, from our based on what the Ministry of Health required, and I want to show you in a little more detail. Also, you can see the roles of each process, but also the pre-requirements we had to meet on the transition between processes and the operation of the processes. So, for instance, before entering ozonation, the MBR had to water entering the ozonation had to be fully nitrified, which we defined as nitrite and ammonia below 1 ppm. And we had to reach a turbidity below 0.15 NTU, which is close to being an imaginary number. It's low to the point where, to the best of my knowledge, there's only one turbidity meter that can be used to reliably measure the slow concentration. And the 0.15 comes from an Australian regulation. The California regulation calls for 0.2. And I cannot describe the amount of discussions we've had with our Ministry of Health, trying to convince them to go up from 0.15 to 0.2, which sounds, needless, kind of, like a huge waste of time. It's almost insignificant, like 0.15, 0.2, what's the importance? But when you're talking about these low concentrations and the need to meet them 90 or 95% of the time, it can actually make a difference. Also for measuring wise, it's a lot easier to measure 0.2 than 0.15, in spite of the small difference. We were required to operate ozonation with a CT of 1. Usually, CT is a very common way to look at disinfection. If you look at chlorine, for instance, for disinfection, you multiply the time, the contact time with the concentration of chlorine, and that's your CT. In ozonation, it's a lot more complicated. It's a lot more complicated to measure. It's not a direct measurement. And that also turned out not to be the easiest way to go. There's another way to look at ozonation effectivity and to decide on your ozone dose, looking at the ratio between TOC and your ozone concentration. So ozone to TOC ratio. Basically, you constantly monitor your TOC levels, and then that's how you know how much ozone to put in. It's a lot easier to measure. It's direct. You don't have to go through reciprocal, like through all sort of like calculus and complicated calculations. But our Ministry of Health demanded that we use a CT of 1. So that's another challenge we had to overcome. And then we also we also decided that the UV transmission, so how much light can go through the water before entering the UV would be 85%. Now that's a number that's it's an engineering design criteria basically. You design your UV system so that it can work in this level of UVT. So if we want to use a lower UVT, we just have to define it for the full scale system. So these are our requirements. I don't have time anymore, right? Okay. So I have a bunch of slides showing the results from running this system for about 2 years. Basically, we managed to tick all the check marks. So we showed that the MBR removes pathogens the way it's supposed to be. It meets its turbidity goals. It meets its nitrification goals. Ozonation removes trace organics like expected. I do have a slide here on PFAS, which might interest some of you. So this is a single sample from several locations taken from the SAT, from soil aquifer treatment, and these are several samples collected throughout the system from the engineered treatment. And there are differences here, but the concentrations are so low that I don't know how real those differences are. And we only monitored 4 compounds. So we need to look into it further, but regardless, we are below 50 nanograms per liter, and the existing regulations in Europe, which is what we follow for PFAS in potable water, is 100 nanograms per liter. So regardless, we are way below that limit, and we're talking about effluent. So we feel okay with that, even though we're not removing PFAS. And just generally speaking, we see the BOD doing what we expect it to do. There's biological oxygen demand coming into the system. It goes to 0 after the MBR. It goes up again after ozonation, and then it goes down again after the back filtration. So we managed to kind of tick all the marks and get the authorization from Ministry of Health to pursue a full-scale facility, which is what we're currently doing. It's turning out to be a lot more complicated than we had expected. So what we're going to have in the future is the shut-down wastewater treatment facility, who's going to still produce secondary effluent, which will go both to the SAT and to the engineered solution. And the engineered solution is supposed to prevent us from discharging to the environment any excess effluent. But also, in cases we do need to release to the environment, then the engineered solution might need to send water that are not good enough to go into the line that goes to ag users. We might need to return it to the soil aquifer treatment. And then it all joins together in a line that goes to the south, and it's used for both in reservoirs and for irrigation. And that's what we've been designing these days. I'd love to answer some questions if I have the time. And also just to say that we are heavily invested in R&D activity in this field, but also in many others. And we're always looking for new collaborators.
Wonderful. Thank you very much, Hadas. We do have a couple minutes for questions.
Hadas, thank you so much for this very informative presentation. I have a couple of questions, if you don't mind. So I am really impressed with the utilization of infiltration tank under the ground. So what will be the residence time in that large storage tank?
So the infiltration is actually not into a storage tank, it's into a natural aquifer.
Yeah.
And the residents that we're actually doing now, and we're now in the process of conducting an experiment to get more exact numbers. But residence time can be anything between 2 months and 3 years, depending on the distance between the infiltration basin and the production well.
Very nice.
The average is about 6 months.
6 months. So what will be the current footprint of this new processes that you are planning to do? How it's going to increase the current footprint of the wastewater treatment plant? Do you have any idea on that?
Yeah, unfortunately, I don't have the numbers, like for electricity consumption. Space-wise, obviously, it's going to be a lot more compact than what we have at the soil aquifer treatment. Yeah, I don't know the numbers for electricity. Yeah. Okay.
Great. Time for another quick question.
I have a question for everybody. So this is remarkable. You have stretched water in a remarkable way. There are a number of places around the country or around the world, so Spain, Portugal, Mexico, that are suffering from chronic, water shortages. Agriculture is taking it on the chin in a million different ways. As you're developing this, are you also thinking about how does this scale and export?
We're not exporting reused water to the best of my knowledge. Oh, export the technology? Okay, so the scheme is unique to us, I guess, but the whole idea of reuse is not unique at all. And I think, like, obviously we're talking about it to our partners, and we are collaborating and partnering with a lot of different water companies around the world, both in the US and in Europe. So we are sharing this and showing them what we've been doing. And they have their own ideas and methods for reuse. And I guess one of the main differences is the necessity of reuse, the scale of reuse, and also the applicability of reuse, because we are lucky enough in the sense that we're a very small country and water is managed as a national resource that we can afford to convey water through 30 kilometers and just do it because we can. In most other places, it's not feasible. It's not feasible that way. It's a lot more complicated. And also, the distance between the place where you treat the water or produce the water and the place where you actually need to use it is larger. So I don't think it's a scheme that can be, copy pasted in other places. But we're definitely inspiring our partners to go that way and to find the best niche for reuse that's the right one for them.
Thank you very much. Thank you very much, Hadas. That was excellent. I think for the sake of time, we should move on. Let's thank Hadas again for a great talk. That was wonderful. Excellent. So we are moving to our second speaker, who is visiting us from a little bit closer, from Purdue University. David Warsinger is an assistant professor in the Department of Mechanical Engineering. He's an expert on thermofluids and on membrane treatment processes. He's been at Purdue. I think you're coming towards the end of 5 years. Is that right?
Approaching 6 now.
Approaching 6 years. Prior to that, he did a PhD at MIT and then a postdoc with Meni Elimelech and Jae-Hong Kim at Yale University. So David, looking forward to your talk.
Thanks very much. Let me grab this. So we already had one PFAS-oriented talk today, and we have yet another one. I'll try not to overlap content here, but we are looking at membrane hybrid systems where we actually have a selective membrane with PFAS destruction. And we were lucky enough to get this to be a cover for ES&T, which shows the overall concept, right? So electrodes sandwiching a membrane. So I'll give a little intro. I'll give a background on PFAS. I'll talk about these new regulations, which will actually be really challenging to address given current technologies. Talk about the methods to treat it, talk about this particular solution, and go into more details on that new method. So my background, I'm mostly not a PFAS person. I'm mostly a membrane person. I do a lot of work in desalination. I also do membranes for HVAC, for air filtration, etc. And most of our work in my group is using thermodynamics, thermal fluids, or material development. And this is kind of a spectrum of many techniques. And so just a brief rundown. So We do weird nanostructure membranes. We do desalination, including the highest efficiency variants with batch RO. Thermal desalination, membrane heat exchangers for HVAC, a little bit of water vapor harvesting, some water and things in space, and also work here in catalysis, which I'm sharing today. So forever chemicals, right? So these are per and perfluoroalkyl substances. We did some of this intro before, but I wanted to reiterate some of these sources, right? So a lot of food products, non-stick on your pizza boxes, fracking and oil and mining extraction using lots of these chemicals and putting it into the groundwater. A lot of furniture and floor polishes that are now being, let's say, made illegal in some places, more in Europe than the US, are sources. A lot of industry sources, including airplanes, and anything that's stain resistant, even your rain jackets that is water wicking, are likely using PFAS. The advantage of why this bond is so good and bad is this CF bond is really, really stable, right? So fluoride is the most electronegative element, which means it can give compounds really low surface energy and can be thus very hydrophobic and thus repels lots of stuff. But then the bond is really, really stable. Our bodies cannot break those down. So there are a lot of costs to PFAS. So, we have issues in dealing with them in water filtration, impacts in agriculture. A major source of this is actually firefighting chemicals. And one reason you'll see all these funding opportunities coming out from the Army is they would use foams that are PFAS based. So basically spraying PFAS foams across an entire hangar. And there are stories of 6 foot deep in foam, and then you just wash it out into local waterways, right? And then, oh, suddenly every major Air Force base is a contamination site. And they say, oh, please remove this from the environment, and we want this in the parts per billion or lower levels. And it's just like, you've been flushing this out for decades. Like, it is a mess. And you're trying to get it out of the environment. Very challenging. So there's blood testing and evidence to show that there's lots of medical effects. It's carcinogenic. There can be brain effects. It's associated with lots of different diseases. You can ask a physician for more about that. One of the concerns is, especially for child development and fetal development. And so for families who are trying to have kids, for instance, they might say, okay, I'm going to live without my nonstick pans for a while, because that can be a potential source. So major issue, very, very challenging. And there's new regulations to deal with this. The key takeaway from this slide is the EPA has recently done new regulations on PFAS. And essentially, all water treatment plants will be required to be monitoring for these compounds by 2027 and will be required to treat them by 2029. So they have some time, but while we can separate them out and have some sorbent that will be a toxic waste product that we have to put in a landfill, the ability to destroy these compounds is actually, I would say, a fairly low technology readiness level. We're not there yet, and this is actually very, very challenging to get to. And it's one of the goals of the Renew NSF engine, and a lot of technology innovation will be needed to get there. So EPA estimates that doing so will save lots of lives and substantial costs if we can reduce our PFAS in the environment in the US. So what are our options to actually get rid of PFAS? So we can remove the water stream and reject it. So this is the separation processes, and we just concentrate it and we have some extra waste stream. In many cases, in conventional water treatment plants, they'll filter out much of the water and they'll send what remains back into the environment. And so they'll actually be essentially concentrating the PFAS and then throwing it back into the lake or river for us to all enjoy in the environment. So we would really like to destroy these compounds. Now, those separation processes, they may be able to absorb it. And so in those sorbents, we'll have this toxic thing to dispose of. But that's our best case, is more nasty toxic landfills. So we want to break these things down. Also converting to sulfates, but fluorine ions, oxygen, and CO2. We're using redox reactions, but it's very challenging. I mentioned this already. The hydroxyl radical, which is the ubiquitous method to destroy stuff in water treatment plants and advanced oxidation processes, actually cannot break this carbon-fluorine bond. So we need alternate techniques. The energy numbers are very, very high. Just for some context, so in desalination, where I really do most of my research, about a third of the lifetime costs are energy. And the available electrochemical process today use more than an order of magnitude more energy than desalination does. So the cost of water, you're talking about substantially more than conventional sources if we have to treat it. So we have the sorbent processes, and we have kind of different ends of these molecules. So a hydrophobic piece and often a charged piece. Some of this compounds approaches to remove them. So granulator activated carbon can kind of absorb the tail, and then selective resins might try to absorb and attach to some of these other functional groups. For filtration effects, these are largely size-based, and we'll basically let these smallest compounds, so salts through, or if you do reverse osmosis, you get no salts through. They take a little higher energy. They typically use much lower flow rates on the membrane, so you need massive membrane areas. For an example, the largest desal plants in Israel or the big plant in San Diego, you can measure the membrane area in square kilometers. So massive membrane areas. And so more capital intensive. All right. And so this is kind of the process that we've been developing. And essentially, we've taken this, we need an anode cathode pair, right? We're able to actually destroy these compounds because we have some electrode that when you apply an electric charge to it, actually has enough energy to destroy and react with parts of these compounds. And so the main innovation here is we're sandwiching a nanofiltration membrane in between the anode and the cathode. And so this will mean that the membrane will concentrate the particles we wish to destroy closer to the reactive anode. In this case, we're using a tin oxide antimony material that was very promising in the literature. So this is what it looks like. And this would be on the top side of our membrane. And we use elemental mapping. We can see that we have the compounds that we said we would have. So in this device, we're also having electric fields applied across this membrane. And remember I said these compounds typically have a charged functional group. We can use that to our advantage. And so if we apply an electric field, we can basically drive the compounds up towards the reactive anode and away from the membrane. And in the reverse orientation, we can actually see that we get strong differences in, for PFOA, the most commonly tested PFAS compound, because it's one of the more well-known ones to be toxic. And we see that we get very good rejection in the standard orientation that shows our charged effects are helping us. And in the reverse orientation, we're actually driving compounds through our membrane. So it's the opposite of what we want to do. So we're seeing strong effects of this electric field combination with the membrane. And we can see that compared to a control, we're getting quite good rejection. So electric field case, we're mostly, where's the laser version? Not very bright. We're getting very high, nearly full rejection of the PFOA. So it's kind of staying in the system until some of the byproducts can be degraded. And we make a mapping of this degradation. So once we're applying higher voltages, and these are fairly high voltages, I will say. So you were looking at a few volts for your systems, right? Okay. And so we can make a regime map where we are getting good rejection, and then we kind of need a certain amount of voltage applied across the anode and cathode to get the migration of PFAS in one direction. So again, what's happening, we have them being attracted to the anode, being destroyed at the anode, and the byproducts, the ideally CO2 and fluorine groups, will be the only ones that can get through the nanofiltration membrane. And we can see that we are increasing the fluorine over time, so we're actually getting full mineralization of these compounds. Now, this is taking a while, right? So we saw before we want to have single pass flows of minutes, but this membrane, we're actually operating around 70 liters per meter squared hour. So it's actually a relatively high flux. So while we basically have very long residence times, which gives us a good destruction, by trapping these compounds near the anode for a long amount of time. And we can look at the breakdown of the substantially smaller chains of fluoropolymers. And we can see that we are actually converting most of our compounds into fluorine and breaking and getting rid of the not only PFOA, but the shorter chain compounds as well. And we're applying relatively high, these pressures, about an order of magnitude less than desalination, but still, this is some energy. It turned out that in our study, actually, we were using more energy for pumping than we were for the electric current. So compared to the really high energy intensive processes, this actually looks very promising. A caveat is that we had most of these studies in pure water, and then only subsequent some studies with some salts present. Pure water has a reduced ionic conduction, and so you're going to spend less energy on your electrodes. And if we look at our water flux for this study, right, we're looking at reasonably high water fluxes and very good PFAS removal. So I think I went through this faster than I meant to, but that's okay. So specialized nanomaterials can destroy and not absorb these forever chemicals. Combining this PFAS destruction allows for the concentration of contaminants near the anode, and it deals with a lot of the transport issues, right? We have a trace contaminant in the parts per billion or worse. And so having this long residence time with them trapped in close proximity to this anode allows us to get good rejection. So we did find when we started adding salts present that things became a little unstable and we need a lot more work in this direction. And then we still were able to achieve fairly reasonable fluxes, typically in the range of nanofiltration membranes and higher than, let's say, reverse osmosis membranes, which would be around 15 on the high end liters per meter squared hour. So I can answer questions. Brian can probably answer the harder questions. And I can also answer lots of other topics on water and desalination, which is more of my background.
Terrific. Thank you, David. You helped us get back on track in terms of time a little bit too, which is good. We have some time for questions.
Yeah, thanks, David, for the talk. I had just a couple of questions on the setup. So when you have one anode cathode pair, and so the electric field is being produced from the same anode that's doing the destruction?
Yeah.
Okay, because I was a little confused at how. So you were saying you're doing this in pure water, so it's just DI water, and you're adding just the PFAS?
So some of the experiments were DI water and PFAS, and then some had sulfate in it.
Okay, because the voltages seem so extremely high that there must be a lot of resistance within the electrochemical cell. Did you ever measure what the actual anode potential was?
I don't think we did.
Okay, because that would be interesting to see what that actually is. And also, I know from the literature that and I think you showed it in your plot, there are nanofiltration membranes that can get 90 plus, even 98% rejection of PFAS, and yours was quite a bit lower. So is there a reason for selecting a nanofiltration membrane with low PFAS rejection versus having one that already has? I mean, what's like the cost?
Yeah, so and generally the nanofiltration membranes vary in their pore sizes, and so we had one that was a little looser than we probably should for this process.
Okay.
So in future work, I would think we would want to use tighter nanofiltration membranes and really not even let the smaller PFAS compounds through that membrane.
Okay, and I mean, do you have any information on your current densities for this process? Because if you're looking to save money there, I mean, it's, the power is the voltage times the current, and probably just placing the electrodes closer together could reduce the voltage and then probably save a lot on the energy of that.
Yeah. I'll check.
Okay. All right. Thank you for the talk.
No, great questions. Appreciate it.
So this experimental setup that you've done have you guys actually in real life done it?
Yeah.
Okay.
That's kind of how experiments go.
Well, the only reason why I asked is I was trying to figure out if it was theory or if you actually did it
Yeah, let me see if I can find more photos for you. So the way that we do a lot of these experiments is we use CNC machining to make channels into a pair of plates that we then attach together. Yeah, this computer seems pretty slow. So the photo I was showing you before, if it will load, actually was SEM of the anode itself. Slide 11. So basically this was a small, it was a cylinder, it was about yay big. My other version I sent has, I think, a photo of it. If we have some time, would you mind actually trying to pulling that from the email? Thanks. Other questions?
Yeah, I'm again new to the field, so forgive me if it's a silly question. Has anyone done some sort of cost analysis as to what additional input energy would cost per unit, whatever is the thing that you want to remove? In other words, is there any calculations whether electrical versus chemical way of destroying PFAS, which one is more economically viable?
Sure. So to my knowledge, mostly only the electrochemical ones. So kind of combining, having basically a catalyst with an electric field applied to it can actually destroy PFAS. And correct me if I'm mistaken there. What I've seen in the literature, anywhere from 30 to 70 plus kilowatt hours per meter cubed, which again is about an order of magnitude higher than desalination. In this study, it was very little energy. It was less than 1 kilowatt hour per meter cubed. I think it would really increase if we had more salt in solution, but it does seem to be potentially relatively efficient. It's also heavily influenced by the concentration of PFAS in the system.
And do you know if I should find out myself, but is there specific antibodies against specific PFAS compounds that you know? Do humans produce antibodies specific to those? Are there biological methods to detect PFAS instead of physical?
No, I actually don't know. Do you know?
She might have it. Because they're like, if you look at the PFAS, they are similar to hormone, right? I mean, they're about the size of the molecule for which probably there's an immune response. And if that is the case, there might be other opportunities to detect.
Yeah. I did get an error from sending it once. Yeah. So maybe
I know there's some labs and companies that are trying to make advantage of those properties for sensors, like, grab, like yes or no question sensors. But I think, I don't know the answer for breaking it down, but I guess if there was a biological way to break them down, they wouldn't be called forever chemicals.
Sensing.
Yeah, so it's one of the pathways that's being going.
Actually, I was sort of researching along that line. So this is very superficial, but at UC Riverside about 6 months ago, a couple of researchers discovered a couple of bacteria that can eat this and make it go away. And the reason I even began thinking about this is that, you mentioned that this is such a tight bond. And I wanted to know, does this ever happen in nature? Or did we have to wait until the 1930s and suddenly we have this? And sure enough, it's very uncommon, but it does happen. And it's been my experience, if it exists, something will eat it. So.
Yeah. And then I actually have a follow-up question. I wanted to.
I think the UC Riverside was not looking at perfluorinated, but polyfluorinated compounds. I could be wrong about that, but that's what I remember when I saw that. Well, PFAS is poly and per, so there's a difference there. And also there has been a group, Peter Jaffe at Princeton, who has shown degradation of perfluorinated compounds. but no one can reproduce it.
Yeah.
Yeah.
Well, that's it. Yeah, actually, yeah, it's a really good question. I actually have Peter's paper open on my computer right here, 2019 ESNT paper, which is really nice, but we'll see if it can be repeated exactly. But so my question actually was the biological. I'm more on the biology side. Biological defluorination has been suggested to be a reductive process, whereas you guys are looking at an oxidative process. Is there also, can you look at the cathode as well for destruction? Can you look at a reductive process as well? Is that something you're looking at, or just oxidative route? Interesting. Okay. Yeah.
I don't have a budget on it yet.
Okay.
We're going to be working together at some point under this new engine. So,
Yeah. Okay. Very good. Very good.
Yeah.
Thank you. Interesting.
Yeah.
Yeah. Very good. Very good.
On
Thank
the
you.
on the biological side, there's no known organisms that are making fluoropolymer bonds in their own structures. It is largely alien to us. Our immune systems have no ways of easily dealing with it. Yeah.
All right, very good. Thank you very much, David. I think we should probably switch gears to stay on track here, but appreciate your talk. Let's give David
Great.
another round.
Thanks very much.
Thank you. All right, our last talk of the day is my colleague Vinayak Dravid from Northwestern University. Vinayak is the Abraham Harris Chaired Professor of Material Science and Engineering. Does great work in a wide range of different areas. He has particular expertise in nanoscience and nanotechnology for energy, health, and environmental applications. He also is really an expert in microscopy and analytical approaches. He runs a couple of centers at Northwestern, the Nuance Center and the Shine Center as well, which are great user facilities at Northwestern. So Vinayak, very good to have you here, and look forward to your talk.
Thank you. Good morning. Shalom, shalom. Very happy to be here. I've been aware of this event for many years, and I'm glad to be a part of it. And I know I'm sitting between the talk and the lunch, so I'll try to accelerate. At the same time, in the spirit of we just discussed, as you're approaching complex problems, I think we do need perspective from all sides. So in that spirit, I'm here. Normally, much of my professional career, I'm in the dark room, inside the microscope, looking at atoms and molecules, and that's what most of the time I've been doing. But a few years ago, we realized that this understanding that we glean out of that interaction, molecular level interaction, has the prospect to actually adapt or anchor to something that is a large enough scale to address this problem. So that's the part that I'll present. And I really want to acknowledge Aaron and George and all others who hold this symposia and all this type of events. I've done some in the past, and I know it's a lot of work, and to be able to pull things together, and to you as well. So I really want to thank all of you, and particularly the organizing committee, for going through this extra effort. And the way things are happening in the world, I think we need more togetherness and working together than the other way around. So with that spirit, forgive me if my jargon doesn't jive with the words that you have used. So I'm more of a material scientist. So that's one aspect that I'm learning from a collaborative group with Aaron and George, is that language, so that we can bridge that skill. Yeah. So the way, I look at it, I deal with electronic length scale atoms, molecules, and most of you are dealing with kilometers and miles and so forth. So I never imagined that we would be in this community bridging the length scale, but I think more than ever, I see tremendous opportunity to bridging that length scale from nano to macro. Somehow it's not moving forward. So let me, it looks like, is it frozen or? I thought it was my magnetic personality, but all right, great. So we call it recover, rinse, repeat, just play with the words. The idea being, can we make a reusable sorbent, if that's the phrase most of you are probably familiar with, so that we can impart some selectivity. And sponges, as you'll see, I hope, an amazing platform that it hosts considerable fluid, correct? But it's not very selective. It picks up any fluid. So if we can initiate the initial reaction or the initial selectivity through a coating, and then combine that with the ability of the sponge to host a lot of fluid, is the idea that we got some years ago. It's a work of several people, several years, over the last 4 or 5 years. And one disclaimer, we have a startup. So part of this work is somewhat related to the startup. And so that's the disclosure. We have a lot of open position. I'm really part of my motivation to show this slide is to really encourage. We're looking for all sorts of partnership, collaboration at all level, some of the technical areas that you see here. And it's not just the permanents or a postdoctoral type. It could be short-term visitors. And I really would love to work with Aaron and George to see if there are opportunities for cross-fertilization of students and staff. Oops. All right, so this is the type of slide you've seen many times, but I always enjoy to see how, this different revolutions that have occurred. The first one that you see on the top, maybe 1700s of the world, 1800s, 1900s. And you can see in the last 50 years, this enormous growth. And some people call it a problem. I like to think that it's great people living healthy and longer lives. And I don't think that's a big challenge. But this obviously is the challenge. You've seen some of this before. And I'm not kidding. Because of the startup, I do go to places like East Coast, West Coast, and the investors, and particularly the work one on the West Coast actually had asked me, is there an app for it? How to remove pollution? You won't believe this level of naivety at times. So there is no app for it. We had to physically remove, and this is the challenge that I never thought that we would be able to meet. Correct? Again, going from atomic or molecular scale to the gigaton that we had to deal with. The other realization last few years, you guys are more expert than I am, is I found out that even to have this so-called transition, renewable, is fraught with challenges because we're going to end up using a lot more fossil fuel for renewable also. So even renewable transition would require considerable. A lot of the pollution problems that you deal with are truly a fossil fuel problem, whether it's oil or methane or gas, natural gas, and so forth. So at least foreseeable future, I think this issue of fossil fuel contamination is going to be here for a long, long time. So there is this sort of a sense of recognition now. I think is something I emphasize to my students, which they had not seen before, is that in a societal development, you have some sort of a equitable development across all energy, environment, and sustainability. And it's great to hug trees. There's nothing wrong with that. But you need to provide some value to see why is this important and why is it effective. And that's the challenge in the environment particularly is ability to sustain the effort. So reuse and recover and those kinds of phrases are going to be equally important. So much of my work has been, as you can see schematically, is to look at molecular scale interaction between fluid surface. We've developed some very innovative microscopy chips where we can look at liquids and gases interacting with surfaces, and we're writing our papers and so forth. But then we realized that some of this can be anchored onto sponge. And sponge is an amazing platform, we find out, as I'll try to show you. And then if you can impart that selectivity, you can really sequester and capture all sorts of contaminants, not just water-based. We're doing CO2 capture, among other things. But what we need actually for it to be effective are some really very basic things, which again are engineering consideration and not as much science. Effectiveness, efficiency, time-wise, in terms of selectivity. Of course, we don't want to create more problem than we solve. So having solutions which are eco-friendly and drop in, that's something I had not appreciated the last few years, is because this is such a entrenched industry, this, wastewater, stormwater, whatever you want to call it, it goes back hundreds of years, if not thousands. So you need, he's already gone up. So you need a system which are just drop in as much as possible, so you don't need to change things. And all of those things you probably know better than I do, but that was a revelation for me. And last but not the least, it has to be economically viable. So we go to, my two kids grew up with this guy, SpongeBob, and it's always very endearing. Other than being cuddly and lovable, Sponge has all its attributes. And all we do is very simple. We take sponge, whether it's a polyurethane, which is one type of sponge, which is generally hydrophobic, or cellulose, which is a lot more hydrophilic. It's a situation where there's a lot of water and a tiny amount of contaminant. We use cellulose, and then otherwise polyurethane. And all we're doing is we're creating an affinity at the pore surfaces with a very dip coating. It's a technology that goes back hundreds of years. The British invaded India and occupied for that purpose of learning how to dye different clothes and impart beautiful colors. It's the same technology going back centuries is what we use. So all we do is, in terms of the range of pollutants, you have nutrients, which I'll show you great data, critical metals, because each metal, I'm a material scientist, we know everything has these certain energy levels. And I think I saw some great insights into electrochemical sequestration. There are ways and methods, some of it are in the IP stage for us, where we can tailor our approaches. I'll show you a couple of examples specific to copper or zinc, and we can be very selective in attracting particular elements. And then there's the generic classes of hydrocarbons, oil and contaminant like fog, fat oil, grease, and MPs, micro nanoplastics, and CO2 capture, and so forth. And you want approaches which are simple, either two things, either water or air flows through them, or you dip them, or you keep them in air, or you dip them in water. No bombs and system, because everything, if you add anything else, that adds more cost to it. So we call it the story of R. So we repurpose. Typically, when you get your holiday gift, you take your iPhone and you throw the rest of it in a landfill. That's foams and sponges. So the first R is the repurpose. Then we have a coating, which I'll show you more about scientifically. Then, of course, the coating implies that you don't need to use a monolithic material. So you're using already a 5% of, it's like no different than the walls of the painting on the wall is really the key rather than the wall itself. So you have reduced, then you expose it to soil, air. I'll focus on water, this being the water symposium. But actually, we have a product where you can actually absorb oil and other hydrocarbon in soil for weeks and months and selectively. Air, the same thing. I'll get to water. So the idea then is that pollutant in the water specific to that particular coating will be sequestered. And we recover that and reuse the sorbent or the sponge repeatedly. And so that's, I think, is the key, is to be able to repeat this so that when you remove that pollutant, you can either monetize it, you can take oil and sell it, or phosphate and sort of make a precursor out of it. And then eventually you restore the environment. And that's the sort of a big picture. So amazingly, we were able to develop several of these. And I never thought that this sponge platform will turn out to be that versatile. So I'll show you very quickly oil spill case of oil removal. In two extreme cases, when there's a spill, there's a lot of oil, versus there's oil contamination, which is just the parts per million sometimes. Then, of course, nutrient, which is primarily phosphate, and I'll show you heavy metals and so on and so forth. So there are two parts to our group. One is the characterization part that you see on the top. And we have an analytical facility I'll show you. You're welcome to visit. We are developing some unusual methods for detection, some of them. Hopefully, I'll tell you next time we meet. And then the second part is the capture and recovery, which is selectivity through sponge-based system. So the first example is this OHM type of coating, oleophilic, loves oil, hydrophobic, hates water, and multifunctional. You see on the bottom right, very obvious, it repels water, is some beautiful pearl droplets of water. So it's very selective for oil. The same thing was done. You put a drop of oil and you see, you can't even see it because it absorbs very quickly. And so on, you see, and just above that is a polyurethane sponge, and you do the 5% coating, and that's where the OHM coating comes. Remarkable that regardless of the type of oil, so on the y-axis is the absorption capacity. So you can see if I have a 1 unit sponge, I can absorb 25, 30 times that weight in oil selectively. So look at the normal sorbents are barely 1. So you can see there is already a 25 to 30 times less material that you need for the same amount of oil. But wait, you can squeeze the oil selectively and reuse it. So you can keep on doing that many times. So you see in the second plot, any pH, it still gives you same level of performance. On the bottom left, you can see number of cycles you keep on doing. It's almost 100% recover. And bottom right is often a lot of spills occur in saline environment, regardless of the salinity, it seems to get the result. Then the company also took this to the next level, because there are many cases where it's not the oil spill you worry about, but also even oil spill itself. I was very surprised that in just 2021 alone, there are 20,000 oil spills that have been documented by the US Coast Guard. It's incredible. But the other end of the spectrum is you have 1% or parts per million contaminated water. And for that, we use cellulose, and same basic idea that this OHM absorb the oil part of it and let the water pass through. And you can see compared to all the other competing product, this seems to do very well. So you have these three attributes that I mentioned that has been commercialized by the company, and it has EPA approval, California approval for use because it doesn't contaminate, and so we're very excited about that. All right, so I always wanted to show this, the Swiss Army knife. So when I first came to America, I used to hear those infomercials at late night, okay? And so you do one thing, and they say, wait, if you order now, you'll get this. I said, oh, it's amazing. I said, wow, you get so many things, right? So what if a sponge does the same thing? It not only removes oil, but it can do other things. And I'll show you the form factor of sponge is so incredible that you can have a very large sponge, or you can have a large sponge, make it into small pieces, you can make them boom. So it's a tremendous versatility. So that allows us to do all sorts of things that I'll show you. So the oil and water is already commercial, things are going well. I'll show you the second part, which is the phosphate, which are at the engineering stage, and we are looking forward to working with our team here. More this, same thing with metals and so forth. Let me start with this pearl media. It came out of one of my students. You know the backstory, so I don't want to waste your time, except to emphasize that I learned so much in the last 5 years about phosphate that I never thought I would. Among other things, the geopolitics of phosphate, you know about the Norway discovery to Ukraine war, and this is the older paper. In fact, there was another article just a year ago on this phosphate and its implication to fertilizer life and so forth. You have seen this story from yesterday's speaker as well. So how do we deal with this? So we start with cellulose, and there's enough material known that, which has very high affinity for phosphate. All we do is we anchor it onto the surface of the cellulose sponge. And all we do it at one particular pH condition, lower pH, you absorb, and it turns out you can absorb almost 100%. It's just incredible efficiency. And all you do is you tune the pH, increase it, and then it releases. And almost 100%. I'll show you a lot of the data. And so just a simple approach for which there's enough literature on. All we did is just anchored it on sponge and made it a little more optimized. And this came out in Proceedings of the National Academy just a couple of years ago, in 21 late. And it was incredible to see the basic science, which I'll show you how that translated into a viable technology in just a matter of 2 years. So what you see on the left-hand side is the absorption capacity, or how much we are capturing. On the left-hand side is, as you can see, is the capture curve. So at lower pH, you get almost 100%. But remember, you don't have to change pH. Even if it is a 5 or 6 pH, that does sufficient absorption to be able to remove a very meaningful amount that from our experimental work that we're doing with several industries. In the middle plot, you see, and you increase the pH, it releases. And initially, it releases the phosphate, but there's an initial reaction that we are monitoring. So we are also looking at the mechanism of why and how it's happening. On the right-hand side, you see the cycles are big. Students get tired after 10 cycles. They're saying we're seeing the same thing. But in the future, we'll be doing much more rigorous, etc. But you can see the dark is the captured one, recovered capture. The first cycle is odd because you form a particular phosphide as a compound on the surface and not the phosphate, and a lot of subtleties which are not as important, but you get the basic idea. So I often show this picture because in microscopy, we see things we've never seen before. I mean, look at James Webb Telescope. We are seeing things that never been seen before because those tools were not available. So sometimes our understanding of this universe, as in the case of James Webb, or water in our case, is informed by some of the new tools and methods and techniques. And so anytime we see results too good to be true, we always take a step back and see what else can we do to make sure. So we do all sorts of characterization, testing, modeling, and eventually, as we hope to be able to do, scale up and so forth. So for that, this is my plugin for the center that was referred to. We develop a lot of analytical methods, techniques. We have SHOP exchange and collaborative programs in all areas of characterization, for microscopy, surface science, and I certainly welcome you to visit, and we'll be happy to show you around. Why do we do this? Because this is what we do. We go from a very low length scale or high length scale of the order of millimeter, centimeter, maybe kilometer. You get the idea. To the next level is microscopic level, so you can see the architecture. Then to nanoscale to see what is the form, function, specific characters of carbon and iron that we use. and down to truly molecular scale. So this is a classic material science. And the key is to bridge this to the environmental length scale on the left-hand side, and that's what we're doing. So this is the example of cellulose sponge. Just to emphasize, you see hierarchical porosity. You have large pores, small pores. All of them have this coating. This ultramicrotome section, very exquisite technique. Happy to tell you more. And you can clearly see a thin, bright line. That's the real coating. And you can see it's less than 5% of the field of view. So very tiny amount is still sufficient to impart that functionality that you see. We do exquisite spectroscopy to really understand fundamentally at the molecular level using X-ray photoelectron spectroscopy to look at bonding and surface information. The details are not as important because they're in the paper already. And you can monitor ironage, phosphorus, and then things like association. So we can clearly see wherever there's iron, there's a phosphorus. So we know there's an affinity of the two. And I'll show you complex situation. And that is the reason why we do all these analytical studies. Then you have to have real samples. So we work with MDRD, Skokie, Metropolitan Water Reclamation, many other. Actually, we have worked with some Florida company. There's another Storm Trap, is a local operation here. And they have access to real sample. And then this is an example before and after. And there's a suspense there because I'm not showing the other things. And this is at the tertiary stage. Again, you know better than I do, where generally biological processes are used for phosphorus. And this is our result using the actual sample. So apparently there's chloride necessary for other things, sulfate, you need bromide for antibacterial, you need fluoride. But you want selectivity against phosphate, and that's what you see. And so what used to be, we've done different levels. This is just one splendid example, and you can clearly see the selectivity of this approach. So we're very excited that this is actual real sample. So can we do something more? Because in the Midwest, particularly, if you remember, I asked the question, in the Midwest, there's a history of smelting, also some metal processing. So copper, zinc is ubiquitous in this. I didn't realize that, in addition to, of course, phosphorus. So it turns out, again, I'm skipping a lot of the detail, but I'll show you examples. So we are working with Storm Trap, is a local company. They're managing stormwater and some others as well, where there's this level of problem. You have phosphorus, you have copper, and you have zinc. And as you can see, this is from my student just a few weeks ago, and almost 100% we can recover both the metals as well as phosphorus. Then we got a little greedy. I said, okay, there's so much, especially in tailing ponds where you can have a lot of amounts of copper, zinc. Can we then recover some meaningful amount and still reuse a sponge and keep on doing that? And it turns out that it might be tantalizingly close. So on the y-axis on the left, you'll see the recovery or the amount we're getting. And the volume is a proxy for time as you are changing the pH. So the dotted line that you see is the pH line. If I can make that. So this is the pH. So it's sort of a neutral, and then we reduce it. Then we are increasing it. And you can see when you reduce it, both copper and zinc come out. But if you see the phosphorus is 0. It doesn't. So you have selective emission or release of the metal only. And then time goes by, we change the pH to high pH, and you can see the phosphorus goes up. So actually, if you see this, this is an accumulated plot, percentage versus volume, almost 90% plus almost 100%. 90%. And I used to be very worried. I said, oh, it's 90% only. There's one phrase I learned last few years, which I'm still trying to digest, is the perfection is the enemy of good enough. And this is something material scientists are not good at. Okay, we want either 2 plus 2 has to be 4, not 4.1, 3.9, right? But here I have to accept that, it's not too bad, but as long as you can do it in a realistic condition. And that's the sort of a psychological adjustment that we are making these days. So that sort of gives you an idea that I don't show you some of the other results, but the point is that we have all of these new contaminants in water that require a very scalable, deployable solution for which we need that level of effectiveness and the time and the scale that we can address. Sponge, in addition, is also a great reservoir for organisms. So one of the things we hope to be able to explore is we can have biological features and functionality imparted within because you can have nutrients in the sponge pore as basically food for bacteria. and you can have colorimetric assay and others. So we're working with Syn Biology Group, among others, as we forward. So again, none of this is possible without fantastic student, and I look forward to working with your fantastic students so that we can make progress from scientific issues to engineering. So with that, I think I should stop and happy to take questions.
Very good. Thank you, Vinayak. That was excellent. Questions, Heather?
Yeah, hi. So your pearl sorbent, that captures phosphate, right? I know that in a lot of places there is serious issue with arsenic in drinking water and groundwater. Have you applied that there as well, since they're such similar?
The answer is yes, of
molecules?
course. And we have a paper that came out. I'll be happy to share with you. I don't know if I have that slide because let's see. So we've done some screening of. Okay, hold on. Skip that. It's a little slow. Okay, yeah. So there's a version of sponge with a coating specifically for different metals, and there should be arsenic here somewhere. So yes, the answer is for a slightly different type of coating, we can have much more affinity for arsenic. And the idea then is there are classes of contaminants, like lead has certain characteristic, transition metals have certain characteristic. And the reason I asked for biology info, because biology is far more specific. You know, an antibody has a very specific antigen. That's not the case in physical systems. So we have a classes of, affinity coatings that we, so there's a one class which takes care of some of the arsenic issue. And then the idea is that if particular water has a different type of contaminant, you cut pieces of different type and mix them, and then you address them instead of trying to make a new membrane every time. So, right.
Yeah, thank you for the talk. I'm curious on the desorption, this pH dependent. Is that related to the speciation of phosphate by pH, or is that a change of the surface by pH?
It's a very good question. And the answer is I don't know for sure right now. And those are some of the questions that we'll try to address. First, we were not even sure that all this would work. So once now it is working to the level of sophistication that we expect, now we're taking a step back and asking this type of question. What are the speciation there is? What sort of other forms of phosphorus? And so we are doing a lot of characterization, and some of this will come out of that. Otherwise, we'll have to adjust some, coating or some other parameters, we hope. But at least the fact that the Skokie water supply, which you would go into the tertiary treatment, seem to be working, that gives us some confidence that it's at least addressing some of the core issues. Yeah.
Well, of course, I've got a question.
Oh.
This is brilliant. It's really, really interesting. And it sounds like you're commercializing it. So can you give me a sense of what you envision, both in terms of, let's say you have a water treatment plant. Do the water treatment plants suddenly become mineral recovery plants as well? Is there another income stream that begins to work here? And what would it take? I mean, right now you're doing little bits, and it's unclear like how often you have to pH squeeze out the sponge, but I'm guessing there's so much junk that fairly often. So how do you see this scaling up? What are your plans for the next 5-10 years?
Great difficulty. That would be the short answer. But the answer is yes, all of these are good consideration. But the way I look at it is that issues such as suspended solid, biofoul, there are strategies in place already where people deal with this. And so if we can have our approach or our technology as a drop-in to, otherwise you would be using alum or some other sorbent, except that we have much higher capacity. And if you so choose, you can remove that, recover it, and reuse it. But there are two classes of customers or people that we deal with. The one who say, we just want to remove it and we get a phosphorus credit, we don't worry about. But then we could think of, if a commercial sense, that we absorb that phosphorus, release it another tank, and you keep on doing that, it might form a brine enough solution that could be monetized for fertilizer precursor. So these are the life cycle analysis, cost analysis type of things that need to be done, and that being done. But first, we wanted to first see whether this approach works in the first place, right? If it does, then you start to, because if it was rhodium and rhenium that's necessary, then we're going to be, dead on arrival, right? So this is sponge, very cheap. This is based on iron, carbon. So economically, we think this should not be an issue. Then market exists. Then it's all the question of engineering. How do we design it? So we're working with the industry to see how best to adapt this type of technology.
Very good. I think for the sake of time, we should thank Vinayak for his talk. Thank you very much. That was wonderful. Very good. And a nice final forward-looking question. That was excellent as well. So I'll hand the floor over to Aaron.
Thank you, George. Yes, I just wanted to say again how happy I am everybody came and enjoyed the very interdisciplinary discussion. You can see there's a lot of collaboration involved and even more needed to reach some of these solutions. I also want to take this brief moment to thank Crystal Felcaro-Heaps, who of course run all the AV, and overcome many challenges, both logistics and then operations. I also want to thank some of the other people who have helped. So Yanka Piper in the back and Aditi Basfetti, and Jordan Price, who had to leave and spent most of her time kind of coordinating everything out in the front of the house.